Okay, thank you. Welcome to this session. I'm Vincent Cocampo. I'm professor at University of Lille in France. And I will share the session with Matthias. She's here. Okay, and so the session is on structural method, dedicated to structural method for fault diagnosis. So we'll have normally 6 presentations, but I don't know if there is someone to present the paper for the 4th paper and the 6th paper. Is there someone to present these 2 papers? So we'll see when arriving to this paper if we have to wait or if the paper are presented. So we will start directly, not to lose time, and start with the first paper presented by Renato Murata. Yeah? And he will present a work on the structural analysis of a rocket multi-engine propulsion cluster for fault detection isolation. So please, for the presenter, don't use the pointer. The pointer, red pointer, because it doesn't work online. You can use the pointer to change the slide only. Okay?
So good morning, everyone. My name is Renato Murata. I'm going to present my work on... And I'm going to present my work on structural analysis of a rocket's multi-engine propulsion cluster for fault detection and isolation. So a brief table of contents. I'll start with an introduction, and then I'll present the multi-engine cluster model. Using this model, we will perform the structural analysis, and then we have some simulation tests and conclusions. So the system considered here is a reusable launch vehicle. And this type of vehicle, it has new needs for thrust modulation. And one possible solution to answer those needs of thrust modulation is to use a multi-engine propulsion cluster, which is illustrated in figure 1. So instead of having only one engine, we have more than one engine. In this case, is the multi-engine propulsion cluster of Saturn V, which has 5 engines, and this configuration is more reliable than a single engine cluster, because if a fault happens, the fault effect can be attenuated using the remaining healthy engines of the cluster. So to attenuate the effect of the fault, it is necessary to build a fault detection and isolation system. So the main objective of this work is to evaluate the possibility of fault detection and isolation in the multi-engine cluster. So the multi-engine cluster model considered here, it's composed of 3 identical liquid propellant rocket engines. Those engines will use liquid oxygen and liquid hydrogen as propellants and operates in a gas generator cycle. So for this study, we consider only the lock side of the multi-engine cluster. And this part is composed of 3 subsystems. We have the lock tank, the feeding lines, and the rocket engines, and where P stands for pressure and Q for mass flow. And the functioning of the multi-engine cluster is the following. Each engine will receive an external thrust reference, and the engines will use the control valves to meet the thrust reference. And according to the opening of those valves, mass flow will be used, and the mass flow that is used by each engine is imposed as the output mass flow, outlet mass flow of the feeding lines, and the sum of the output mass flow of the feeding line is imposed as the output mass flow of the lock tank. And on the other hand, the output pressure of the lock tank is imposed as the input pressure of the feeding lines, and the output pressure of the feeding lines is imposed as the input pressure of the rocket engines. In addition, the thrust that is generated by the engines, they will generate acceleration of the rocket, and according to the rocket's acceleration, it will also have an influence in the output pressure of the lock tank. And we consider faults in 2 subsystems, the feeding lines and the rocket engines. So I'm not going to present all the equations to model, but just the variables. So we have, for the tank, we only have one variable, which is the output pressure of the tank. For the feeding lines, we have the pressure and the mass flow for each line. And for the rocket engines, in total, we have 14 variables. It's not necessary to understand all of them, but the rocket engines, as I said before, it operates in a gas generator cycle. It means that the rocket engines has two combustion chamber, a small one that is used to generate the thrust, no, a big one that is used to generate the thrust, and a small one that is used to generate energy to pump propellants to the main combustion chamber. This small one is called gas generator, and we use the G to denote this. So the first four variables of the rocket engines, they are mass flows of oxygen and hydrogen that enters either the combustion chamber or the gas generator chamber. Then we have four pressures that denotes the outlet pressure of the turbopumps and the outlet pressure of the turbines. We have two mass flows to denote the output mass flow of the turbines. And then we have the rotational speed of the oxygen turbopump, the rotational speed of the hydrogen turbopump. And finally, we have the pressure in the small combustion chamber, which is the gas generator, and we have the pressure in the main combustion chamber. And each engine has four control inputs, which are the control valves. So we have VGO, which is the valve that controls the oxygen mass flow in the gas generator, and VCO, that is controls the oxygen mass flow in the combustion chamber, and the same for hydrogen, so one valve for the gas generator chamber and one valve for the combustion chamber. And the faults were considered in the feeding lines, they were leakage, so we consider a leakage in each line. And the faults considered in the rocket engines, the first one is oxygen leakage in the combustion chamber, an external oxygen leakage, and the other three faults, they are additive faults in the control inputs. And just to illustrate how those faults were injected in the system, here we have the equation that describes the evolution of the pressure in the combustion chamber. It's a simple equation where a constant multiplies the sum of mass flow that enter in this combustion chamber, and we just subtract the fault to simulate the effect of the leakage, the oxygen leakage in the combustion chamber. So using the structural model, using the model that we presented, we performed the structural analysis of the multi-engine cluster. So the structural analysis is a powerful tool that gives information about the possibility of fault detection and isolation, and then it can be used in early development phase of FDY systems. And to do so, we have to construct the structural model, which is a bipartite graph that considers only which variables are presented in each equations. And then there are efficient algorithms that can be used to analyze the model. In our case, we use the fault diagnosis toolbox to perform the structural analysis. And then we perform in two different measurement scenarios. In the first scenario, we consider that we have only measurements, pressure measurements from the feeding lines. And in the second scenario, we consider that we have those measurements plus some measurements from the rocket engines, which is the rotational speed of the turbopumps, the pressure in the combustion chamber, and the pressure in the gas generator chamber. And we also had the mixture ratio in each chamber. So for the scenario 1, we wanted to investigate which faults we could detect and isolate it using only pressure measurements from the feeding lines. So we performed the Drummond-Meltonson decomposition of this system. So this decomposition rearranges the system equation into three parts: the underdeterminate, just determinate, and overdeterminate parts. And only the faults that affects the equations that are in the overdeterminate part of the system can be detected, because in this case we have more equations than unknown variables, so we could use those equations to check consistency. And to analyze which faults could be isolated, we can analyze the equivalent classes, and the faults that are in the same equivalent classes cannot be structurally isolated from each other. So the results of our decomposition is illustrated in figure 3. The overdeterminate part of the system is illustrated by the big blue rectangle, and we can see that all faults are in affect equations that are in this big blue rectangle. So all faults can be detected using only the pressure measurements of the filling lines. And the equivalent classes are the gray rectangles, and we can see that only the leakage in the main line, FM, could be isolated from the other faults. Consider the second scenario where we have more measurements, which includes the mixture ratio in the combustion chamber, which is the ratio between the oxygen mass flow and the hydrogen mass flow. We could detect and isolate all faults, as we can see from the fault isolability matrix in figure 4. So once we define that, we know that every fault can be detected and isolated, we pass to the next step, which is the residual generation, and we consider as residual generator candidates the minimum structurally overdeterminate set. There are some efficient algorithms to compute the MSO sets from the structural model. The MSO sets are subgroups of equations from the overdeterminate part of the system, and it has a degree of redundancy equal to 1. So the number of equations is equal to the number of unknown variables plus 1. It means that those sets, they can be solved independently, and they are affected only by the fault that has a direct impact on the set of equations. And another characteristics is that the number of MSO sets increases exponentially with the degree of redundancy of the system. For example, in scenario 1, where we have less measurements, we had only 10 MSO sets, and for scenario 2, consider only measurements from one rocket engines, we have more than 40,000 residual generator candidates. So we consider scenario 2 because it's a more realistic measurement scenario, because usually we have those measurements. And we face a new problem, that is when we have more, as we have more than 40,000 residual generator candidates, we don't need all of them to detect the faults that we considered. So we have a problem of select the best candidates with the highest sensitivity. So we proposed a practical algorithm to select those, to compare those residual generator candidates in order to find the candidates that are more sensitive to the faults. So we consider two things. We consider that each output is measured with different measurement noise. In the case of the multi-engine cluster, from the most to the least accurate, we have the rotational speed of the turbopumps as the most accurate measurement that we have, and the mixture ratio in the combustion chamber as the least accurate measurement that we have. And we also consider that each fault has a different impact on the outputs. For example, the leakage in the combustion chamber will have a bigger impact in the pressure in the combustion chamber than in the pressure in the gas generator chamber. And then we proposed a practical algorithm that that finds the candidate that uses the most sensitive outputs, and in theory that those candidates will also generate more sensitive residuals. So this algorithm is based on the signal-to-noise ratio, and it returns the fault detection index. So a residual generator with a bigger fault detection index should be, in theory, more sensitive to the fault than a residual generator with a smaller one. So some simulation results. So we implemented the multi-engine cluster model in Simulink in closed loop around the operation, nominal operation point, which is 1,000 kilonewtons for each engine. And we injected 3 different asynchronous faults. The first one is a blockage of 5%, the nominal value of the hydrogen valve of the gas generator chamber. The second one is a blockage of 25% the nominal value of the hydrogen valve of the combustion chamber. And the third one is a leakage of 5% the nominal mass flow that enters the combustion chamber, the oxygen mass flow. And we arbitrarily selected 3 MSOs to generate residuals. Those MSOs, they were generated using the sequential residual generation method. And here are some information about those MSOs. For example, the MSO 180, it is composed of 15 equations. It uses 5 outputs and is in theory sensitive to only 2 folds. From the faults that we injected in the system, this MSO is only sensitive to the oxygen leakage in the combustion chamber, FQCO. So on the left, we have the fault detection index for each residual generator and for each fault. And on the right, we have the residual signal. First of all, from the residual signal, we can see that each residual generator is sensitive as it was defined before. For example, MSO 180 is only sensitive to the third fault that we injected, which is the leakage in the combustion chamber. And we can see also that this MSO, it has a bigger fault detection index than the MSO 64. And we can see from the residual signal that the residual generated by MSO 180 is more sensitive than the residual generated by the MSO 64 for fault FQCO. So some conclusions. So the simulations results have proven the utility of structural analysis for fault detection and isolation in the multi-engine cluster. The fault detection index correctly predicted the most sensitive residuals, even if there's room for improvement in this algorithm. The FDI approach could be applied for a larger number of faults, including actuator and sensor faults, which is the case for upcoming articles. And a more robust residual generation method could be used. In our case, we use the most simple one, which is the sequential residual generator, but we could use state observers. And finally, a qualitative residual selection algorithm could be combined with the algorithm that we propose that evaluates the residuals and could provide subsets of residuals that could detect and isolate all faults. So thanks for your attention. Those are some references.
Thank you. We have time for question, 1 or 2 questions. Do you have? Yeah?
Yeah, I'm curious about this index. Is that computed, could that be computed without generating the code and running the residual?
Sorry?
What do you call it, index?
Yeah.
Yeah. Could you compute that without running a residual?
Yes, like in theory, we consider that the residual generators that uses the most sensitive outputs will give in theory more sensitive residuals. So we only analyze the which outputs are used by the residual generators, and the residual generators that uses the most sensitive outputs will be in theory more sensitive to this fault.
I mean, you generated some residuals in the end.
In the end, I generated...
Have you validated this index against the signal-to-noise ratio in the simulations?
Those, like here we have the index for each fault and the residuals that we generated. So in some cases, like for the leakage, it's very clear the difference. For example, the index of MSO 180 is much bigger than the index for MSO 64 when we are detecting the leakage. However, for example, for the valve fault, we have a bigger difference, but this bigger difference is not visible in our residuals, even if it appears to be a little bit more sensitive. It's only a qualitative analysis, but That's why we have room for improvement, because we didn't consider the inputs that those residual generators are used.
Okay, thank you very much.
Thank you. Only a little question connected to this question. I don't understand how you can compute this index and what's the meaning of this index without computing the residual, because the output intervene on a given way in the residual expression. And so it depends on how the output is computed and how it what is the influence of this output in the residual expression. So I don't understand how you can manage this and consider this in the structural analysis point of view. Because your algorithm is only on MSO, if I clearly understood.
Yes.
So you don't compute the analytical expression of the residual?
No, I just use data that was generated in simulation to compute this detection index.
Okay.
Yeah, if I could use the expression in the analysis, it will give a better result, I imagine.
Yeah, sometimes it will work, but sometimes it could not work because of the sensitivity of the output in the expression of the residual.
Yeah.
Okay, thank you. Thank you again.
Yes, so the next presenter will be Vincent Conquepot with the presentation Improving Residual Robustness to Noise for Fault Localization in a Y-shaped Network.
No, not this.
Because we are sending
Okay.
otherwise we send only we use
Okay, so I will present this work, which is a collaboration between two laboratories. One is an automatic control laboratory, which is my laboratory, and which is a Crystal. And we are working for a long time on fault detection, fault detection isolation, with residuals, with structural residuals, structural method, and so on, and models. And the collaboration with colleagues from IEMN, which is an electronic laboratory, and mainly on communication and communication system and transmission information around in a network. So they are working on signal-based methods. They are working on different kind of method, and our aim is to propose some efficient method for fault diagnosis for communication networks by mixing the two approaches, so the two point of view from electronics and from automatic control. So this work has been done by in the context of Abdelkarim thesis, and it is entitled Improving Residual Robustness to Noise for Fault Localization in a Y-shaped Network. It's not exactly on structure analysis, so we use structure analysis to derive the residual. We use for complex network, but this is a work that is connected to this, but to show that when we are working in structure analysis on structure from a structural point of view, we don't have all the information on the sensitivity of the residual, and so we need to improve the residual after generating this residual. So the outline of my presentation will be the following. First, I will recall the context and objective of our study. I will come back on the general view of what are the methods for wireframe network diagnosis. I'm working on models, so I will present the model of a line, and we will see if it is possible to use this model with electronicians that don't use the model, and what could bring this model. We have developed a method which is named the transferometry-based diagnosis method, and I will present the principle of this method, how to improve the residual for the residual to be more robust to noise, and I will conclude and give some future work. So, network control systems are complex distributed systems with different kind of devices, sensors, controllers, and actuators, and ECU, so computing interface. And so this network control system is known as this, but one important component of this network control system is a wire network, so the cables that connect the devices together, and to transfer the energy from one device to another one, and to transfer the data from one device to the other one. So it's a very important component in network control system. You see the cumulative length in different kind of applications. So we don't consider mainly in fault diagnosis, we don't consider mainly the cable when we are dealing with diagnosis of network control system, but it is one of the most important components. And so we are trying to do some work on this, because there is few work done on this topic to detect and isolate fault in these cables. So fault in cables. So we know that cables are in very harsh environment condition, and they are submitted to stresses, to constraints, mechanical constraints. So they are due to the humidity, to the heat, to the chemical contamination, to the mechanical stress, it makes the cable degraded. So we can have thermal degrading, insulation cuts, and so on, which correspond to what we will call soft fault or degradation. We use the same term, even if there are some differences, but we use the same term in this work. And this soft fault will continue, will pursue their evolution into hard fault. And we want to avoid this hard fault, because when we have a hard fault, it's short circuit or open circuit, and the cable cannot be used, so the data cannot be transferred and the energy cannot be transferred. So we want to detect as soon as possible the soft fault that occur in the cable. So we consider that soft fault, when we have soft fault or degradation, we can still have the transfer of data and energy with no modification. We can transfer, so we cannot see directly the effect of the soft fault on the data that are transferred. Directly we see nothing, we have the data, we collect the data from the receiver and don't see precisely that what happened. Of course, when we have hard fault, as I explained before, we can see directly the failure, so this is not our topic here. So what is our objective in this work? We try to design and implement an online monitoring system, so that will work during the operation of the network control system to detect the soft fault as soon as possible and track their time evolution. And we also want to locate, so to isolate the fault, so to locate the faulty branch in complex network. This will not be the case here, because I will take a simple example, which is a Y-shaped network, but we have done the work for very complex network using structural analysis and decomposition of the network. And we want to locate the faulty branch, but also, if possible, where is the fault in the faulty branch. So different methods exist in the literature for fault diagnosis. We have offline method. Offline method has visual inspection, infrared thermal imaging, X-rays, guided ultrasonic wave. But this is offline method, and we don't want to use this kind of test and this kind of inspection. So we want to develop online method, and the well-known method is reflectometry method. And we have tried to develop another method, which is named transferometry. There is little work on this kind of method, and we want to see if it is a good way to make fault diagnosis, to use for fault diagnosis. So only some basics to know what is reflectometry and what is the principle of reflectometry is very simple. I think everyone can know this principle. We send a shared signal from an injection point. The signal is transferred into the line, and because of the change in the impedance locally due to the fault, a signal is reflected and come back to the injection point, and we analyze this, the difference between the sent signal and the received signal, and can estimate what is called the reflectometric transfer function, reflectometry function, which is the S11 coefficient, which is a frequency-dependent function. So this is the main principle. I show that only to understand clearly what is the transferometry method we use. We send exactly the same kind of signal. We can send exactly the same kind of signal. I will explain that we will do another way practically. But we send a signal, and there is a transmitted signal and a reflected signal. And due to the fault, which modifies the impedance locally at the position of the fault, we have not exactly the same transmitted signal as the injected signal, and so we can analyze what is called the transmission coefficient, which is a transfer function and which is frequency dependent, and the name is classically in the notation is S21 or H. We will see that later. So two ways to obtain this transmission coefficient, the estimation online of the transmission coefficient. We can use vector network analyzer, which is a classical instrument, and so we inject with this instrument, and the VNA compute the transmission coefficient, the reflection or the transmission coefficient. So this is one way that could be used, but which need a VNA to be implemented at each point of the network. So it's not practically what we want to use, because we want to work on a transportation system, and so embedded network control system. So we use another way to estimate the transmission coefficient using the power line communication principle, which is, the principle is to send the data through the line, so to inject not a shared signal, but inject the data, specific data from the injection point, and analyze what is received at the reception point. And with that technique, we can estimate, and the PLC, so the power line communication technique, include necessarily the estimation of the transmission coefficient. So it is included in the method. When you implement a PLC method, you can estimate, you have the estimation of this transmission coefficient. So we use this because we are working on transmission and communication system, in embedded system. So we have the computing. We have this computation using ECU. At each point, we can implement the power line communication system. So, why using a model? So, I will explain that, because normally we don't use a model. Electronicians don't use a model. They send signal, they receive signal, and they analyze what they receive. We use model for two main reasons. So, we use model to have a proof of the sensitivity of what we will have as a set of indicators, so it will connect it to the transmission coefficient we estimate, and so we will generate residuals, and we will prove that some residuals are sensitive to some faults, some set of faults, and other residuals are not sensitive. We will prove that from a structural point of view. So we did that for many very complex network, and can generate structured set of residual, which is not easy to do when we are thinking only, when we are using only signals. So signal-based method, we make some measurement, but the analysis is not so simple to see where we should inject the signal, where we should have the reception of the signal. So we use model, but only to prove the structural sensitivity. So we prove that the residuals are potentially sensitive to fault, but we will not use the model parameter, which are the network characteristic. We will not use for residual computing. We will use signal. So we'll use PLC, power line communication, estimation. So the estimation of the transmission coefficient through the PLC system. We suppose that we don't know the length of the cable, the characteristic of the cable, because we don't know practically that. When we are working in embedded system in cars, for instance, we don't have the length of the cable. We know that there are cables, but it's very difficult to have the precise knowledge. So model, I will go very fast on this. It's only to say that we have model. It's very simple to obtain. It's an electrical circuit. And so we have the source, we have the receiver, and we have what is called an ABCD matrix with L, which is the length of the line, ZC is the impedance of the cable, and gamma is the transmission factor. So, okay, we have this model. We can, for a line, we can have this model. It's very easy. We have developed also, we have think, what is the modification of the model when we have a fault, a soft fault. So we have two kinds of faults that could occur, and we can represent this into series fault or parallel fault. And this may make some local ABCD matrix which are quite similar, but we study only the series fault in this work, but it's quite similar to use parallel fault. So by combining all the part of the network, so we have nodes, we have different branches, we have faults, so we can connect all the matrices and have the global model of the network. So from this ABCD model, we can estimate the coefficient, the transfer function. So it's very classical computation. So what is the fault diagnosis method? By using this estimated, the model, we can prove the following expression of the transmission coefficient. And we have, okay, some parameter, but we will not use this parameter later, but only to see that the parameters are present. So we have the expression, we can derive the expression, and we define one indicator, else indicator, which is this expression where H reference corresponds to the transmission coefficient when the network is not faulty, and the H test is the transmission function when there is a fault, so possibly a fault. So we define this and obtain this result by using the expression of the transmission coefficient with respect to the model, and so we obtain that some indicators are zero, others are not zero. And S0, S1, S2 are the different source points that could be used in this network to send information from one point to another point. From this, we define residual, which is the difference between two indicators at the same source, and obtain the structural table of the residue. So this is very important to note that if we have a fault, for instance B0, so the residual will be in the plan. So it's really structured residual as we know for classical FDI method. So we use a benchmark, so we develop a benchmark where we can put some faults in some elements of the network. So it's a Y-shaped network, so on this form. And so we can inject different kind of faults and have some data. So we obtain a lot of data. We made a lot of computation, a lot of estimation, and so we obtain this position of the residual, so in the residual space, and obtain some cluster corresponding to each fault. And with we can see clearly that when the branch B2 is, for instance, B2 is faulty, so we have the residual in the plan B2, and the amplitude of the fault makes the residual more bigger. So this is what we see at the first time, but when we are making a zoom on the residual, we see that the residual are not exactly zero, even if they should be zero from the structural point of view. they are not depending on the parameters, they should be 0. But due to the noise, and the injection of the noise, which is a nonlinear injection, the residual are not 0. So we use a classical coefficient, correlation coefficient, which is used for analysis of electronic field. So to compare two frequency signals, so it's a correlation, and we built a mixed residual by considering this factor of the multiplying, so this weighting factor. Yes, 1 minute. I will conclude. So only to explain why it works. So in a healthy network, the frac in this are close to 1, so it doesn't change the initial residual. In a faulty network, if the two compare health indicators are similar, the residual is multiplied by the weight, whose value is near 0. So the robustness of the residual to the noise is enhanced. And if the two compare health indicators are not similar, the residual is multiplied by a factor near 1, and so the practical residual are not changed compared to the initial one. So the sensitivity is not changed. So we obtain this. It doesn't change in this plan, but it changed in the other plan. So you see that the red residual was the initial residual we obtained, and by using the 1 minus frac coefficient, we obtain the blue residual, which are 0, and which is what we should obtain. So as a conclusion, we have developed a method by mixing tools from automatic control and from signal-based processing and communication system. We obtain a set of structural residual for fault isolation, and we prove the sensitivity of the residual. And practically, we have seen that the result is not perfect, and so we have improved the residual with a coefficient which is a classical coefficient.
So we run out of time, so maybe when the next presenter prepares, we can have a short question.
Yes, hi. Just a very practical question. Do you have to inject the signal cable by cable, or you can consider all the generally the cables are all together, and so
we send in all cable. Yeah.
At the same time.
At the same time, yeah, of course. Yeah.
Yeah, but then so the method then is explodes. Isn't it exponentially growing with the number of cables?
Yes, and that's why we decompose the network into several parts and consider several Y-shaped networks. So we decompose a bus, for instance, which is a more complex system with different Y network, and step by step we go into the main branches that we want to explore.
Okay, thank you.
Thank you.
Thank you very much. And then
So, thank you. Next speaker is Haman?
Yes.
Yeah, Haman, and he will present his work, and so I give him the microphone to give the title.
Great, thank you. Well, I timed myself, and I was a bit over the time, so I think maybe I could have gathered some of your time, but I think that shit has passed. So I'm trying to summarize, maybe I'm going a bit faster. Thank you for the presentation. I'm Arman, and I'm here to present, the collaboration that we had in Linköping University from Sweden with Scania, the manufacturer and producer of heavy trucks and buses for transportation system. The project is about the implementation of, development and implementation of a diagnosis algorithm on the fuel injection circuit, on their heavy-duty trucks. First, a presentation outline. I will talk about the fuel injector for the people that are not familiar. I will talk about the the focus of this diagnosis implementation and the limitations that were basically dictates to selection of some specific type of algorithm that we had to employ in this work. I will talk about three different data-driven regression model that we use in this work: one-step predictor, state space, and neural networks, which is my own research field as a PhD student, implementation of this neural network regression models also. And at the end I will present the detection and isolation performance of the development that we had. So, so what is the fuel injector is probably like every car owner will realize that in the combustion engine there should be like a precise amount of fuel to air ratio that should have been delivered into the combustion chamber. And this value is for every gram of fuel you should have 14.7 gram of air. And any mixture density that is above this value will consider it a bit of rich mixture, and well, in the long run you will have higher fuel consumption and unwanted emissions in your exhaust gas, and any value below this will eventually leads to poor acceleration, or like if you sit in a bus and you see during the idling, during the engine is on but the bus is not running, you will see some vibrations. This is due to this calibrated amount of fuel to air ratio. So the purpose of this injection system is to maintain the proper amount of fuel delivery. And now, like a self-disclaimer, is that the bottleneck of the diagnosis in this system is actually the injector itself. But normally these injectors are going through a regular maintenance in the workshop, so any clogging or the broken O-ring are normally getting replaced throughout the regular maintenance that the vehicles are going through. What is normally is not the case and needs, and this is the focus of this diagnosis system here, is the injection circuit. The system that basically connects the fuel tank, the optimization unit, into the injector. And we are focusing on detecting faults and isolating faults from the system. So what is the fuel injection system? You can see here the schematic of this system. The whole purpose is to provide constant pressure in the common rail that is connected to the injector. Since the calculations from the electronic control unit comes from the assumption that the pressure is maintained at the constant level, so the vehicle can adjust the fuel amount, dosing amount, basically despite of the workload or the engine is sweet. So maintaining this constant pressure is actually the purpose of this circuit. But two main components can actually lead to malfunction in this scenario. The first one is the degradation of the high pressure pump that is responsible to bringing the pressure from 3 to 5 bar into almost 1,000 bar. And over time, these components will go through degradation, and it will reduce their efficiency. And the other one is clogging in the main filter. The filter that we have in the low pressure circuit can also lead to malfunction in the system. I also need to focus that the limitations that we had in this diagnostics was that we had to limit ourselves to the available signals from the electronic control unit center. So we call it equipmentless workshop diagnosis, so there is no need to add an additional signal from the technician into this diagnosis. So we capitalize on the information that we already have from the ECU. But on the other hand, since we are actually in the workshop scenario, we can adjust the pressure in the common rail. So as I said earlier, the purpose is to keep the pressure at a constant level, but in order to capture the dynamics, we had access to changing the operating conditions in the high pressure rail. So actually we get to excite it enough, so we get the system ID properties that we are looking for. So our approach was to develop a consistency-based diagnosis. We wanted to not only detect the faults, but actually have a way to isolate and separate these two components from each other, as it was a demand on the project. So our approach was to, first, initially we had the idea of developing an accurate model so we can use it and basically use the submodels to develop our residuals. But two main factors actually restricts this accurate development. First of all, we didn't have access to all the detailed data sheets of the existing components due to varying components in different case studies and also the confidentiality of some of the components. And the other part was that including the dynamic in the injector was actually asked us to add the dynamic of the micropulsation that happens in the injector, which also basically adds a new level of complexity, which basically reduced the accuracy of our model. So the idea that we had was basically let's replace the accurate physical-based model with some sort of a data-driven regression model. So we still keep the a physical understanding of the input-output from the structural model, but the features that we feed into any of these regression models are actually derived based on the physical understanding of the system. So it's not an accurate physical model, but we hope, because we imitate the actual causality that happens in the model-based diagnosis, we actually get to learn the causality between the input and output instead of only the correlation. So, well, how did we do it? Was basically, well, the schematic was developed based on the access on the components that we had. We derived basically standard model component for each of the segments, and using those components information, we get to develop a structural model from the system. And since the purpose of using this data-driven regression model is to only train them based on the system working nominally, meaning, well, the system works in the healthy status, we get to collect the data when the system is actually working properly in its nominal condition. On the other hand, in order to imitate the test scenarios and the available faults, we were actually having access to a degraded components actually through adjustment or replacement of the healthy components with the broken ones, not only with broken and not, but actually in different amplitudes. And we actually gather data from different fault components, but we use it only during the test and evaluation, but not during the training of any of the models. As the first, I will not go into details of this part, as the first presentation actually touched upon this. This is the structural model that we developed based on the dual March-Mendelssohn decomposition. We get to actually separate this full model into different submodels, 11 MSO sets. And well, theoretically, each of these components were associated with different fault sensitivity, each of them based on the fact that they use different sets of equations and they follow a different computational graph. Well, theoretically, they should have been sensitive to different sets of faults. And between those, 4 of them actually get the properties that were quite suitable for us with the integral causality. So we get to implement all the model-based regression models that we had in mind. This is not an equation-heavy presentation. It is almost the only one that you need to get to see some equations, so please bear with me. Three different residual models we employed. The first one is Arch model. I think it's people are quite familiar with this. Well, we call it one-step predictor. The point of using this model is that they are generally having good accuracy in the prediction since they use the same signal from the previous samples in its prediction. The other one was the state space form, and the last one is neural network one. Well, the two latter forms are more comparable to the accurate model-based diagnosis. So in a way, we wanted to compare the different residual approach, and compare different detection and isolation performance regarding those. So very briefly, here on the top part, you will see the performance of two of the selected residuals that we made on the three regression models that we had. Theoretically, each of these residuals should have been sensitive to only one of the faults, as it is provided in the middle scatter plot. Well, our observation was that the ARCS models are normally very good at detecting different faults, but when it comes to the isolation, we realize since they capitalize on the previous signals, they normally lose some sensitivity to specific important features in the input domain. The neural network one was helpful on some instances, but generally we had since they are dealing with highly complex nonlinear models, we had the problem of out of distribution for most of our test sets, which makes them quite in some cases we couldn't use them properly. And on the lower plot, I present the performance of each of these residuals on detecting faults, actually based on different relative fault magnitudes. If you remember, I mentioned that we had access to adjust the degraded components to imitate different level of degradation over time. And we realized in most of the cases, the detection of the extreme cases were actually quite feasible, but it was quite challenging to detect the low degradation values. How much time do I have? Is it good? Okay. I will. There was just so in order to, since we had the possibility of detection over time, and the fact that the faults happens in a sequential order, actually we get to use that information by implementing like a detection algorithm that uses the sequential properties of faults happening. So we realized that by just simply adding some sort of accumulating fault effect, for example, a QSUM test, you could have actually detect the faults that they were supposedly should have been sensitive to. Again, the problem of lack of isolation in some of the models would have been prevailed. Well, as a conclusion, we realized that the model-based diagnosis would have been helpful in the design of the data-driven models. Well, we basically didn't have to go through a feature selection because the MSOSS already did that automatically for us. And the use of a change detection algorithm was kind of a mandate in detection of the lower magnitude faults. The main benefits of using this method is that we can normally have access. We can train these networks only using the nominal data, which is in most of the industrial cases is the case, that you have access to the system mostly in the healthiest status, and you want to detect the anomalies regarding those models. And some message is that not necessarily a good prediction accuracy in the training set will lead to a good isolation and detection performance at the end. So there were some tuning and some adjustment needed at the end. Of course, I didn't have time to go into all the details, especially in the detection and isolation performance. So I hope I got your attention enough that you go and actually go and read the paper if you want to learn more about how the faults has been actually affected and detected at the end. Also, the model order and the hyperparameters has been tuned in a way that it can be reproducible for other future cases. And I think it will be beneficial if you are having similar cases today and you want to approach this method in a methodological way. And if you are interested in the way that the structural analysis system works and the way to develop this consistency rates diagnosis, my colleagues' work on development of a toolbox is, I think many people here in this community is actually familiar with. It's quite helpful. And the last one, if you are also interested in the implementation of the neural network-based residuals, which is my own research line, I would also recommend you to go and read my paper. It happens to publish in this conference 2 years ago on the type of regression models we call gray box network, something in between a model-based and purely data-driven models. Yeah, thank you. And if you have any questions.
Thank you. Is there someone to present the next paper? Yeah, you can perhaps install your... Okay, so we have time to ask one or two questions when she's downloading his paper, his presentation. You have a question?
Yes, from your slide number 9, I understand that the neural network residual is...
Yes. You removed it. I think I should put it back.
I shouldn't ask.
Sorry. Slide number 9. Yes.
Yeah. From what I see on the bottom right, I understand that this neural network residual is not really good.
Yes.
Yes. How do you explain this?
Good point. So again, we train these networks on a training set. So we get to train these networks on a training set that is based on the system working in its nominal operation, right? So there is a chance that if you try to test it on when the degradation happens or any fault happens, there is a chance that the distribution of the data is completely out of the distribution of the training set. So in this case, the trust that you have in the detection is actually quite low. So in case that we had to disregard the out-of-distribution data set, we end up having problems with actually acceptable diagnosis from the neural network base. This problem also prevailed a bit in the ARCS model, but also I need to say that the threshold that we set here is actually based on how good the prediction accuracy is in the training set. So if the prediction accuracy is quite good, we had to adjust the threshold so we get a certain rate of false alarms. So in some of the models, for example in the state space model, the prediction accuracy was not quite good, but we are also forgiving in the threshold. So we had a quite low rate of false alarm anyway. So the combination of that and the effect of the fault, it actually leads to better detection in some of the cases compared to the others. So we were a bit more critical in the neural network-based models because we don't know the nature much. So if you have to do is we have to disregard some of the diagnosis output from the neural networks. Yeah.
Okay, thank you.
Okay, so the fourth presenter. The fourth presentation is model-based sensor fault detection and diagnosis in closed-loop power converters for electric vehicles. And the presenter is Galeb. Okay.
Federica Galli.
Okay. Is a sixth presenter here as well? The last presenter? Okay.
Thank you very much. Good morning, everybody. Thank you for following this session. I'm here today to present the work of colleague. My name is Federica Galli, and I'm presenting the work of Youssef Ashra and the rest of the team. Unfortunately, he couldn't be here, so I'm presenting his very interesting work. You may have questions at the end of the presentation. I'm not sure I will have the answers, but I'll do my best. So the topic is about model-based sensor fault detection and diagnosis in closed-loop power converters for electric vehicles. I will start with an introduction and overview of the problem. Then I will show you the proposed model in the in the context of the proposed problematic. And then we will move on to diagnosis techniques for this kind of issues and the selected technique. And finally, we will look at the results and a little summary. So, as far as the introduction is concerned, we are speaking about DC-DC converters to convert from DC current with different voltage. This kind of equipment is used for many different applications. We mostly have to convert the DC current of solar panels and battery banks for end users like electrical vehicles, AC motors, but also like residential areas, industrial applications. So it's a kind of important piece of equipment, and the issue is that whenever a fault happens in this link point of the global net, well, everything else is going to be affected. So it's really important to be able to monitor these kind of systems and detect sensor faults. In this case, so we are focusing on DC-DC converters. We can identify two types of topologies. We have non-isolated and isolated topologies. You can see the scheme here. The two topologies are normally compared in terms of weight, efficiency, EMI, current ripple, and the range of the input voltage. In this work, the CUK converter was chosen. It is quite low in weight, volume, the efficiency is good. There is some electrical magnetic interference, but also the current ripple and the voltage variation are good. So, a state space model was proposed that takes into account of the two modes of this DC-DC converter. In the first mode, the switch is closed and the diode is open, and here you can see all the state space matrices, variables, input and output. The second mode concerns the switch that is open and the diode that is closed, so the opposite. And again, all the mathematical formulation could be obtained and coupled with the previous one. So an average model was proposed where the mode 1 and mode 2 were combined going through the duty cycle. And finally, all the system is proposed in a closed loop control system configuration. So you can see here the system, then the Kalman filter, and the LQR controller. This is the general scheme. We will see it again later. And now we will move on to the diagnosis techniques. So, if we go into literature, we can identify three different types of techniques. We have model-based, hardware-based, and knowledge-based. Research was conducted and the selection was performed according to the indicators that you see at the bottom, like robustness, detection speed, the fact that it has to be applied to a nonlinear system, and so on. And the final choice went towards model-based, in particular Kalman filtering. So the proposed technique focuses on sensor faults. The Kalman filter was chosen because it's accurate, reliable, and it is not sensitive to measurement noise. And the obtained results will be analyzed both in open loop and closed loop to be able to draw an interesting comparison. So here we see again the closed loop configuration scheme, and in particular we focus on two signatures, the epsilon at the output, signature 1, and then we have signature 2 that concerns all the relative rates of change. Now, as far as the results are concerned, in the Kalman filter, we have two steps. We have the prediction step and the update step. Since this work focuses on sensor faults and not component faults, during the simulation, the fault of the sensor was introduced as a bias. And later on, we will see how it is made sure that this methodology is sensitive to sensor faults and not component faults. Here we have two examples. So we have on the left the open loop results and on the right the closed loop results. Sensor faults were simulated as a 3% bias that you can see here in the two circles. The bias arrived after 0.02 seconds of time. In the graphs at the bottom, we can see multiple things. So in 1 and 4, we have the real output and the estimated output. The real output in blue and the estimated output in orange. What we can see is that in open loop, the estimated output reaches the real output quite fast, but there is an overshoot. In the closed loop configuration, the situation is different. The LQR controller was, his parameters were selected according to an optimal configuration, and we can see that there's no overshoot, but the estimated output takes longer to reach the real one. Now, graphs 2 and 5 concern the detection of the fault. You can see with the dashed line the fault detection threshold. And what we can see is that when we go in the open closed loop configuration, the residual that is computed here in blue is bigger. What we can see is that in open loop, we have a spike that is not present in the control loop, and actually this behavior, the spike behavior, makes it more difficult to detect the fault. So we can see how the closed loop configuration helps the detection, and how the fact that the fault is on the sensor, because if we look at the state variable and at the rates of the state variable, we can see that they are quite, how to explain it, we don't see any, especially in the, the only graph that doesn't, that don't have the number, we can see that there is no significant variation, and this gives us feedback and information concerning the fact that the sensor is on the fault. Now, the approach was proposed also with some simulation where there was no bias on the sensor, but some aging on the components. In particular, they applied aging on the capacitor and on the switch. What you can see here is that the computed residual in blue do not cross the fault detection threshold. So this result proves that the proposed methodology is indeed sensitive to sensor faults, but not to component faults, which was the objective since the beginning. So, to summarize, they proposed a technique for the detection of sensor faults in closed-loop control configuration with Kalman filtering. The residuals were generated and used for fault detection with a specific approach. The propagation of the fault detection in the closed loop provoked a modification of the residual which helped the detection task. And for the future, their perspective preview to apply this methodology and improve it for sensor component faults in VSI and filter, and also in the overall conversion chain. Here are some references. I hope I could provide a clear presentation. Thank you for your attention.
Thank you very much. And we have time for questions.
I can try. do not hesitate to contact my colleagues if you have any very deep question, just in case.
Maybe I can start with a simple one then.
Okay.
Just the sensors that you were talking about, which type were there in this system?
This is a good question, but given that I did not work directly on the project, I don't know. I'm sorry. I don't know if my colleague put any information in this previous slide. No, I'm sorry. But I do remember he said something in the article, so maybe you can find some information there.
Do we have any more questions? I also was curious about, you said that the closed loop improved fault diagnosis. Have you thought about why?
Yes. So the thing is that when we have a spike like that, it doesn't leave much time for detection. So over here, with the same threshold, there is a little bit more time to detect the fault. Thank you.
Get slower dynamics or something.
Yeah. The error is propagated in the loop, so somehow the trace is left longer.
Okay, thank you.
Thank you.
Do we have any more questions? Should we go to the next speaker? Yeah, one more question. Okay. Okay, let's thank the speaker once more.
Okay, so next presentation, data-driven soft sensor based on sparse rational graph attention network for hot street meal process. And it will be presented by Shu Janyi.
Yeah.
Okay, thank you.
Sorry.
Yeah. Don't use the pointer. Don't use the pointer, only the...
Point this?
Yeah. No. This one, the two. No? Yeah.
Oh, okay. Thank you. Hello everyone. Thank you all for being here today. My name is Jianye Xue, and I'm from the Department of Automation, Tsinghua University. The title of our paper is Data-Driven Soft Sensor Based on Sparse Relational Graph Attention Network for Hot Strip Meal Process. I'm very glad here to share our work. Next, I will walk you through our work in 4 key sections. First, I will give you a brief introduction of our work, and then is the details of our method, and then I will show you the experiment results. At last, I will conclude our work. First, I want to introduce the hot strip meal process to provide the basic the background information of our work. As shown in the left figure, the hot strip meal process is a critical process in the steel industry involving multiple units such as the reheating furnaces and the rolling mill. And in this process, the produced steel plates should meet some specific requirements, mechanical properties requirements. So the online measurement of the mechanical properties is very important. The current methods for measuring the mechanical properties can be roughly divided into 3 categories. That is the sample analysis and the online analysis instruments and the soft sensor methods. Among these 3 types of methods, the sample analysis is time-consuming, and the online analysis instruments always require high maintenance cost. recently, with the development of the machine learning and the neural network, so the self-centered methods become more popular. In the self-centered methods, mechanism-based methods require precise mathematical model, which is not available for the host-rehearsal process. So, and with the development of the neural network, the neural network-based self-centered methods are more popular. However, the existing works doesn't extract and utilize the specific structure information among the variables. The structure information means that a variable in the process may connect with other few variables, and other few variables can provide additional information to explain this variable. Motivated by this, we propose a special relational graph attention network for the self-censor of the mechanical properties. In our method, we first learn a special relationship among all variables, and then the special relationship and the process data are fed into the graph attention network for the prediction of the mechanical properties. Next, I will introduce the detail of our work. Our proposed method can be roughly divided into two components. That is the spatial relational learning module, which aims to learn a spatial graph structure among the process variables, and another module is the graph attention network-based mechanical property prediction module, which aims to combine the process data and the graph structure to predict the final mechanical properties. In the first spatial relational learning module, we first transform the graph structure learning into an optimization problem based on the graph autoencoder as shown in the left equation. And we utilize the L1 regularizer to prevent the overfitting. To solve the left problem, we translated this problem into an augmented Lagrangian direction to transform from an optimization problem with confluence into an optimization problem without confluence, and solve this problem using the gradient descent method. After we get the adjacency matrix A by the graph autoencoder in the left equation, then to spice this graph structure, the adjacency matrix is fed into a spice max transformation component as shown in the right equation. By this equation, we can spice the graph structure. It means that the small in the matrix A, the small value, the position where is the small value is set as 0, and the other position and the value in other positions is reserved. In this way, we can get a spatial graph structure AS, and this graph structure is used for the subsequential graph attention network-based mechanical property forecasting. In the second component, that is the graph attention network, we first calculate the aggregate representation of the process variables. That is the left equation. And we use the attention mechanism to highlight the information. We think that the aggregated representation consists of the information of the variable and the information from the other connected variables. After we get the aggregated representation, and then is fed into a fully connected layer to predict the final mechanical properties. In the training phase, we utilize the mean squared error between the predicted output and the ground truth to calculate the loss function and optimize the parameters of the neural network. In the experiment part, we first construct a hospital process dataset, which was collected from a real Iran and steel company to evaluate the performance of our work. In this dataset, it contains 5,056 samples. 80% of the samples are used for the training, and the remaining 20% are used for the validation. To improve the training efficiency, we use this score to normalize the data. The performance of the data is evaluated using 3 statistical induces. That is the root mean squared error, mean absolute error, and the R-square. The regression result is shown in the left table. From this table, it can be seen that our proposed method outperforms the other 3 approaches in terms of the statistical indices. And from the right finger, the axis of the right finger is the real value of the mechanical property, and the y-axis is represents the predicted value of the mechanical property. From the right finger, it can be seen that compared with other baseline methods, the points predicted by our method, that is the red points, are significantly closer to the diagonal line, and there are few spots with large prediction errors. This indicates that our proposed method is feasible and effective for the mechanical property online prediction. At last, our proposed work can be concluded into 4 points. First, we propose a no-wall graph neural network-based self-sensor method named the SAFEPROCESS, which can online measure the mechanical properties of the hospital mirror process by using the process variables. And the second, in our model, we propose a space relational learning model to learn a space graph structure in a reasonable and explainable way. Third, based on the learned space graph structure and the process data, our model is built by the graph attention network, and which can achieve excellent mechanical property self-measurement performance. At last, the experimental results demonstrate the effectiveness and the security of our proposed method. Okay, that's all. Thank you for your attention.
Thank you for your presentation. We have time for questions. Any question? Perhaps I have one question. You consider real data, so from an industrial process. Did you have to perform some pre-treatment on the data, or did you take directly the data and compute with this data, or did you make some pre-treatment of the treatment? Some data analysis and to modify the data before processing them.
Okay.
I saw you have to normalize the data. Can you explain that and perhaps do some other treatment?
Okay, I see. Our data was collected from the company, and then we should select the variables which is from the experience, and then the data should be filtered because maybe some data is missed, and this data can't be used directly for the training of our model. After filtering the data, and then we normalize the data and split the training dataset and the test dataset to train and evaluate the model.
Okay. Is there any question? No? Okay, thank you. Hypergraph. Okay, thank you. You take the microphone? Or?
Yeah.
Yeah.
So, hello everybody. My name is Carlo Vitucci. I'm an Ericsson system developer and industrial PhD student at Mälardalen University in Sweden. And today I'd like to introduce one of the outcomes of our research, that is a deductive fault analysis method based on hypergraph. The background. The background of the research is the famous fault tree analysis. I think that any of you knows about it. So I probably wouldn't spend so many words about it, but it's just to recall that these are graphic methods for the loss of function probability and analysis of the criticalities of the component in a system. And what I would lay out is three, let's say, possible cons of using the fault tree analysis. Is a graphic method, so as any graphic methods, once the system is going to grow in complexity or in a size, also the fault tree analysis is very, very big. And that creates some problem in the readability of the result. It's at least not so obvious to identify common failure sources, unless you don't have some specific tool able to do that. But as a graphical inspection, it's very difficult. And by definition, is using the logic gate. So it's, if you miss this knowledge, if you miss the skills, obviously, it's impossible for you to use it. We define a method focusing on removing these three cons from the fault tree analysis. Our method started from basically the same starting point of the fault tree analysis, the definition of the function under the analysis. So which type of system function we want to analyze by means defining the loss of function probability and the criticalities of the devices. But then we are using a concept that we call the failure path. That is a subset in your system able to set a failure condition for the whole system. So basically, we are extracting information from the topology of the system. It's a bit complicated if I try to explain like that, but then it starts to be simple if I use an example to show you how it works. So let's start from an example. Let's consider a system that is a dual motor tribal redundancy control system. Is an exercise, of course, but give us an opportunity to see how we start to identify the failure path. Any of these two blocks, the gray and the blue block, is a failure path, because if they are in a faulty condition, the whole system doesn't work. So we can start to build a matrix based on this consideration, where we can put in a column the construction of the failure path. So a gray block in a faulty condition is a failure path, and a blue block in a failure condition is a failure path. And then we start to make a kind of iteration from the block. So any of these blocks start to be a subset or subsystem, if you like. And then we analyze what we call failure chain. So which type of subset in this subset can we define? And so we have a top and down, basically, starting from this. It's very simple to identify these two blocks for the gray part and two blocks for the blue part. And then we start to build again. We are retuning the matrix. That is an hypergraph representation, of course, of the system. And both of these subsets need to be in a failure condition in order to be a failure path. Because if you have only one motor that is in a faulty condition, that doesn't represent the failure path. The system continues to work with the other motor. And this really is continuously iterating. So, for example, we can identify for the top part of the gray area that we have 3 different components. And any of these components, if in a faulty condition together with a backup solution, is a failure path. So we can retune again the matrix by structuring and also, of course, pointing to which type of subsystem need to be in a faulty condition in order to create a failure path. And since our system is in a static B state, the matrix is a binary matrix. So either a component is working or a component is in a faulty condition. We set 1 for component in a faulty condition. And we can again reiterate specifically to be sure that we are considering the right topology for the failure path. And if you remember, one of the problems was to identify a common failure, a common failure status. We use the analysis of the triple redundancy system to show how it's simple actually to identify a common source of failure. Because, for example, in order to, if you are not familiar with the triple redundancy system, basically you have to consider in a faulty condition 2 of these compute or monitoring system concurrently. And of course they need to stay on a different path. So a common path, come one and monitor one concurrently in a faulty condition is not a problem because the voter to work needed to value. So if you have a wall path in a faulty condition, still it's not a failure. It's a part of the triple redundancy system. But we are building, using exactly the same approach, a matrix from this subsystem, and then we can easily identify any possible duplication of the failure condition source, because a common column is not accepted. So we are going to make an examination of the matrix and basically removing a common column. Duplication of the column is actually a duplication of the failure source. We can remove it. So it's quite easy in this way. So at the end of the day, we have our final topology representation of the system. It's an hypergraph, of course. And the matrix is built on a binary matrix because it's a bi-state system. So 1 means a faulty state for the component, and 0, that is not mentioned in the slide, means that the component is working. It's not mentioned because using the hypergraph in this way, any column represents a failure path. And we are only interested in the failure path. So the vertices represent the component in the system. And so we can start to use a very simple maths to calculate both the probability of the failure, both the probability of a loss of functionality, and the criticalities of the system. We are using a very simple mathematical representation. So you just need to make a product of the failure path component. Any failure path component has its own loss of probability. The product of the loss of probability, the probability of the loss of functionality for the failure path, and then just sum the result. This is the system loss of function probability. And for the analysis of the criticalities of the component, you just have to consider the minimal cut set. So it's you just have to count how many components you have per failure path, and the minimum number represent your criticalities. For example, if you can see in this picture, obviously the fact that we have 2 modules is a critical condition for the system, because if both are in a failure condition, the whole system doesn't work. So you have to put a better attention or a better quality requirement for selection of the motor, because if both are in a faulty condition, the whole system doesn't work. So in order to validate the maths that we are using the fault tree analysis. So it's a kind of course, we expect that the value is the same. We made some simplification in the calculation just for simplicity. Really it's a math, doesn't make anything. But we are using the same loss of function probability for computing a monitor processor. We are defining to have the same loss of probability, loss of functionality probability for the motors. I will leave you to see that it's actually the same. If you are familiar with the fault tree analysis, you can do this. Otherwise, it's really not so fundamental to go into details here. Few conclusion. Obviously, as probably you can recognize, the idea is to create a very simple way to create an autonomous calculation of the loss of probability, removing the dependency to the graphical representation and removing the dependency to the logic state. So once you have an autonomous way to make a calculation of the loss of probability, then of course it's simple to support the designer. You can imagine that behind this there is a tool the designer can use during the design phase to have some support in the decision making. So you can immediately verify what is the quality of the product that you are designing, what is the criticalities, invest more in the criticalities if you cannot achieve your quality requirement. So that is why we think it's very useful, because then you can immediately start to using this tool to have a feedback on your design without really going through the verification team. It's something that you can do by yourself. And in the opposite, the verification team is, of course, facilitated by this type of activity, because the quality of the product is obviously better. Yes, so I think this is over. So if you have any questions, please don't hesitate.
Okay, thank you very much. Is there any question? Yes, no? Yeah?
How would you incorporate correlated events in the analysis?
Event?
Yeah, I mean, if you have correlation between component failures or...
Yes, I mean, if you are thinking two different devices, for example, to be concurrently in a faulty condition, that is present by the definition of the failure path. Because if only one device is in a faulty condition, that is not available in a column, because it's actually the correlation between the devices that create the failure path. So a single component in a faulty condition, if you think, for example, to the redundancy state, a single processor in a faulty condition, that is not something we have to consider, because it's not a failure path. So in that sense, it's simplifying a bit, but you need to have a bit of knowledge in the topology of the system to take this conclusion.
Is there a question?
Maybe follow up if you have like ambient conditions that affect probabilities, like high summer temperature or something.
Yes, that's a good question, because, well, in this presentation, as I mentioned, we have a statics and a B-state system, so we are not going to see the probability of the failure changing because of the different condition of the temperature, humidity, well, you know. But it's definitely interesting, and actually I should mention that we have three evolution of this tool. One is really the basic tool to support the static system. The other one is try to consider not B-state, because once you don't have a B-state system, then you have a probability that is changing in the time. maybe, of course, fault tree analysis is not the best. Actually, it has no consideration of time at all, so it's one of the limits of the fault tree analysis. We didn't analyze so far if this could be also the drawback of our system too. But yeah, definitely it's of course it's very interesting, both dynamically consideration and of course also the probability to have a kind of change of the probability. But that's not done yet. Not done.
Thank you. Other question? No other? Okay, so thank you.
Yes.
So thank you for attending this session. We had 6 very nice presentations, and enjoy the conference. And I think it's quite time for the lunch. We are 5 minutes early, so I think it's okay. Thank you.
Introducing you. This session is entitled Fault Diagnosis for Nonlinear Systems. I'm Vicente Puig, I'm the chair, and I have as a co-chair Fabio. Okay, no problem. So I repeat again, no problem. Welcome to the Fault Diagnosis for Nonlinear Systems session. I'm Vicente Puig, I'm the chair. I'm here with the co-chair Fabio Previdi. And unfortunately, the first paper was not shown. Now we move to the second paper that is entitled Estimation of Cornering Stiffness using Ultralocal Model and LP-based Observer, and will be presented by Daniel Phoenix. Well, let's take this one. Okay.
Thank you very much for a nice introduction. My name is Daniel Phoenix from the Institute for Computer Science and Control, Budapest. So my title of my presentation is Estimation of Cornering Stiffness using Ultralocal Model and LP-based Observer. Let's start with the outline of this presentation. As you can see, I will give you a short introduction to this research and the motivation of it. And then I will give you a brief introduction to the model-free controller, or ultralocal model, or intelligent PID. Then I will talk about the observer design for estimating the slide slip angles of the vehicle. Then I will give you a simulation example of the proposed observer design to show the operation and effectiveness of the proposed method. And finally, I will summarize and conclude the paper. So let's start with the introduction and the motivation of this project. In the era of the autonomous vehicle, the estimation or the measurement of the side slip angle on the front and the rear axles is pretty crucial. However, it is pretty expensive, and it's a hard task because we need an optical sensor to accurately measure the side slip angle, or we need an observer estimation algorithm to estimate the side slip angles. In this project or research, we use the classical bicycle or single-track lateral vehicle model, but a reformulated or modified version of it. I will present it later. And we use this reformulated model to design an observer, And to eliminate the other unmodeled and nonlinear effect of the vehicle, we used a ultralocal model to deal with this problem. Using this ultralocal model, we will calculate or update the cornering stiffness of the model. So let's start with the ultralocal model or model-free control structure or intelligent PID. It is a relatively new control structure. It was introduced, let's say, 20 years ago, and it runs by several names, as I mentioned, such as ultralocal model, model-free control, intelligent PID, etc. So how it works? We have a so-called ultralocal model, which is denoted by the letter F in this presentation, and we have a simple model. Y is the output of the system, U is the input signal, and alpha is a free tuning parameter of the system. We compute the output of the system, not the output, derivative of the output, which is denoted by the nu, and we compute this ultralocal model. And we, let's say, inject or use this ultralocal model as an additional control input to the system to eliminate the unmodeled or nonlinear dynamics of the system. It is pretty obvious that this ultralocal model cannot guarantee any tracking performances. Therefore, we need an additional controller, such as PID or LQ or other control structure to guarantee the accurate tracking performances. So this structure has been used for several control problems effectively, but in this case we want to use to improve the performance of the observer. Therefore, we do not need this additional controller, which is denoted by the letter C in the slide. So we only use the ultralocal model part of this structure. Now let's jump to the vehicle model. As I mentioned, we use the well-known single-tech vehicle model, which consists of basically two equations. The first one describes the yaw motion of the vehicle, and the second one describes the lateral acceleration of the vehicle. Within the brackets, the slip angles are defined. We have two slip angles, one on the front axle and the second one on the rear axle. The other variables in these equations are the yaw rate, which is denoted by the psi dot, side slip angle of the COG, center of gravity, which is denoted by the beta. Delta is the control signal, the steering angle. C1 and C2 are the cornering stiffnesses, which are a linearized version of the tire characteristics. L1 and L2 are geometric parameters of the vehicle, and Vx the longitudinal velocity. And M is the mass of the vehicle, and I is the yaw inertia. So this model has two or three states in general, which are the yaw rate and the lateral velocity, or the beta, the side slip angle. So it does not contain explicitly the slip angles. So we modify this model to reformulate these equations to get the slip angles as the states of the model. As I mentioned, within these brackets you can find the slide slip angles, front and the rear, and here are denoted by alpha R and alpha F. We can calculate the yaw rate signal and the side slip angle in this way using the side slip angles. If we take the derivative of the first two equations, we can get this two other equations. Note that the Vx longitudinal velocity is constant or fixed during the derivation. And the next step, we can extract the equations and we can get these two new equations. As you can see, it appears the derivative of the control signal, the steering angle appears in this equation. We can approximate this signal with a constant parameter. And the letter F and letter FR are the lateral forces of the vehicle, which is computed from the side slip angle and the cornering stiffnesses. So here you can see the state space representation, which has two states, the alpha F and alpha R, the side slip angles of the vehicle. And this state space representation is observable using the lateral acceleration of the vehicle, which is a well-measurable variable. That's why we choose this variable as the output of the system. So using this state space representation, we can design an LPV observer. The scheduling parameters of the state space representation are the Vx, the longitudinal velocity, and the CF and CR, the cornering stiffnesses of the front and the rear axles. So basically, it's a simple design method to get a LPV observer for estimating the side slip angles. So what is the problem with this observer? The cornering stiffnesses, CF and CR, are not measurable. Therefore, we have to approximate or compute or estimate those variables. Here is the main steps of the design method. So as I mentioned, we need a nominal model. We have to discretize this model, and we can design the LPV observers presented in the previous slide. In the next step, we have to choose the output for the ultralocal model and the derivative order. In this case, we have chosen the U rate as output for the ultralocal model, and we chosen the derivative order to 1, which means we have to calculate the derivative of the U rate, which is the U acceleration. In order to calculate this derivative, we use the Alien filter algorithm. We also have to tune the parameter alpha, which is a free parameter of the ultra-local model. And the next step, we have to compute the cornering stiffness of the vehicle using the ultralocal model, which will be presented in the next slides. Here you can see the interconnected algorithm. I have already talked about the L, which is the gain of the LPV observer. We have an LPV model, and I have not talked about these ultralocal-based cornering stiffness estimations, which is the next step of this algorithm. So how can we compute the cornering stiffness from this ultralocal model? The next first equation shows the general form of the observer. Here we have the LPV gain, and when we use the ultralocal model to improve the performance level of the general observer, we have an additional term, as you can see here, which goes through the matrix P using the output of the ultralocal model. So actually, we can extract the subtract the two equations, and we can get this state, let's say state error. Here you can see the matrix A of the LPV model, which can be divided into two parts. The first matrix contains the part that is linked to the CF and CR, the cornering stiffnesses, and the second part does not have any connection to the cornering stiffnesses, so we can eliminate this part, and we can use only this related matrix. We can extract the CF and CR, the cornering stiffnesses, and in the next step, we can compute the state deviation. From the state deviation, the delta CF and delta CR, which are the update or the additional term to the cornering stiffness, which will correct the initial cornering stiffness values. So we can do this calculation at each time step, and it will converge to the real value of the CF and CR. Of course, the CF and CR can change during the operation of the vehicle, depending on the lateral acceleration and the road condition, such as on a low-moved surface, it can drastically change. Now I would like to show you a short simulation example of this observer design method. We have conducted this simulation in CarMaker simulation software. Sorry, it seems like I haven't changed the title of the slide. So here you can see the test track and the longitudinal velocity of the vehicle, which was set to 20 meters per second, but it can be overwritten by the CarMaker inbuilt driver in order to guarantee the stability of the vehicle. In the next slide, you can see the lateral acceleration, steering angle, and the yaw-rate signal during the simulation. As you can see, the lateral acceleration is about 7 meters per second, which is close to the peak value of the physical limits of the vehicle. The yaw-rate signal also shows that the vehicle is close to its physical limit because the maximum value is around 0.6 radian per second. And here you can see the main results of this research or simulation. We actually tested the LPV observer without the ultralocal model and with the ultralocal model. When the vehicle is close to its physical limits, the LPV observer cannot estimate accurately the side slips angle. However, the combined method is able to track or estimate the side slip angle with a quite high accuracy. And in the last slide, you can see the cornering stiffnesses and the tire characteristics, which is calculated from the cornering stiffness and the slide slip angle. As you can see, the initial value of the CF and CR was around 120,000 Newton per radian, and the algorithm can estimate quite well the changes during the test track. And in the last figure, you can see the tire characteristics, which is pretty close to the CarMaker's output. So I would like to conclude the contribution of the paper. Actually, this result, it is the first results of a research. We have just started. We have several other questions we wanted to answer, such as the stability of this algorithm, and we also wanted to use another ultralocal models to improve the performance level of this system. So, thank you very much for your attention.
Is there any question? Yes.
Thanks for the nice presentation. So I have very basic question. So you talk about model-free control. You talk about model-free control, but you do use the ultra-local model. So my question would be, what's the difference between the ultra-local model and the complete model? Yeah. No. I guess there is a difference between ultra-local model that you use and the model that may be real, exact. So what's the difference in this? What kind of physics do you forget?
Actually, the ultralocal model is a basic.
No, I know this this approach of using model free. This approach is in the sense of Cédric Juin, right?
Yep.
The works of Cédric Juin and Michel Fliess. So, but in this context, what are the considerations? What kind of dynamics you consider in the ultra-local model, and what do you forget? Like, what do you neglect?
So what was the unknown dynamics or unmodeled dynamics of the lateral vehicle mod, or what you mean exactly?
Let me reformulate. So your motivation is to use model-free control, right? Because you don't know your model.
Actually, the ultralocal model, but it runs by several names. Ultralocal model, model-free control, intelligent PID, it has several.
So that's where perhaps my confusion comes. Model-free control you want to use because perhaps you do not know your model, right?
Yeah.
But you do use an ultra-local model.
It's actually the same.
So that's where my question comes. Why would you call that a model-free control if you are anyways using an ultra-local model? And if that ultra-local model is really ultra-local, what kind of dynamics have been forgotten?
It's a pretty good question.
I mean, it's
to be honest. So actually, this control technique runs by several names, and it is not really model-free control. It just named it for some reasons. So it uses a ultralocal model, which actually does not contain any known dynamics of the system, but just try to approximate it using this ultralocal model.
Cédric Juin won't be happy to know this answer. I suggest you, yeah, we can discuss later.
It's a very good question. The side slip angles, the two, I'm a bit curious about the timescale. I could see something going in 60 seconds. I wonder exactly what this means. When I drive my car, for example, I know the side slip angles are going to be in the form of seconds. Why so many seconds? Why is the time so extended for the side slip in both cases? No, you have. I looked at the time scale, and the side slip is changing over 60 seconds. This is remarkably long.
Long?
Yeah. I would have thought a few seconds would be.
Here?
Even an aircraft would be not as much as that.
It can change at that rate if you are close to physical limits of the vehicle. So let's say the lateral acceleration is around 0.8 g, something like that. It can change pretty.
Are these the side slip angles?
No, sorry.
No,
it
side
is
slip
a
angles.
cornering stiffness. I'm sorry.
Yeah. If you look at the time scale there, you've got sort of quite a lot of seconds. It's a fraction of getting up for a minute, in one complete change in side slip. The time scale I would have thought would have been much faster.
I was imagining that the dynamics is faster.
dynamic should be faster. Yeah.
You can see which kind of route that were you simulating. Probably something with very long curves.
Yeah, actually I showed it on the first.
Okay, that's fine.
It's a track. Okay. Yeah, it's a
Thank you again.
So let's go with the third paper that is presented by Vicent Puig. The title is Zonotopic FDI Approach with LPV-based EKF in Autonomous Vehicles.
Thank you very much for the introduction. This is a joint collaboration between our university and also an industrial partner that offers the possibility to collaborate in the implementation of the approach that is described in this paper, that is the Renault company. So the two last authors are from the Renault company. So the outline of the presentation is as follows. First, I will introduce a bit the motivation of this research. Then I will introduce the real vehicle we were using during the paper. Next, I will introduce the proposed approach that is related about the use of LPV. This is a little related to the previous paper. And using the zonotopic approach that was presented yesterday in the plenary by Christophe Combastel. Finally, we'll introduce how this approach can be used for fault detection and isolation in the context of this autonomous vehicle, and we'll see some results and conclusions. So one of the concerns in the autonomous vehicles is the safety, because if some of the elements that are critical for the control present some faults, the safety of the vehicle is not guaranteed. And in fact, in the industry, this is one of the concerns, how to guarantee the safety in the vehicle, and of course, in the vehicle when drives in the roads and has to coordinate with the other vehicles. But in this paper, we'll concentrate only in the safety in a single vehicle. In fact, one of the benefits that people justify the use of the autonomous vehicles that can reduce the human error and reduce the number of accidents. But of course, we have to guarantee first that the vehicle operates in an autonomous, safe manner. In particular, in this paper, we will focus in the safety in the module of a state estimation that is used for navigation. That is one of the critical elements in any self-driving car. And the speed measurements, that are two of the sensors we have in the vehicle. And we'll assess the validity of the proposed approach in a real vehicle, first in simulation and then in the real platform. So for testing the algorithm, motivated by this collaboration I was commenting at the beginning, the vehicle is a real one, it's a commercial one, it's a Renault Zoe. But here you have the picture in the installations that Renault has in Spain, in Valladolid. And we can see all the instrumentation that has been added to the vehicle for the testing. In fact, the company already has an autonomous control system that is commercial. Still is not in the market, but in the future they plan to provide this model. So the sensors, that are the elements that we want to deal with in this research, that we will concentrate regarding the faults, are the GPS, the speedometers, that are the odometers in the wheels, and the leaders. There are other sensors for the other purposes, like cameras, ultrasonic detectors, that are not part of this research. For implementing our full detection and isolation scheme, as also in the previous talk and is in many papers in the literature, the approach that we are investigating here is a model-based one that uses the classical now bicycle model. It's quite well accepted in the literature for control, and in this of the model. Why this approach is used? Because this approach can be very easily integrated with the set-based techniques that we'll use later. As also it is explained in the talk yesterday. So to deal with the uncertainty, in fact also in the stochastical manner, there are some linearization techniques that do more or less the same, but using Jacobians. Here instead of using Jacobians, we use a nonlinear embedding, and there is no approximation as in the classical extended Kalman field. So the next idea is that using the zonotopic Kalman filter that can be easily extended to this LPV model, just propagating the center. This is the equation of the center, where there is a gain that propagates in a similar manner as the classical Kalman filter, but using the formulas of the zonotope. Using the covariation of the zonotope, then we have equivalent formulas to the classical stochastic Kalman filter, but without the assumptions that we do in the classical stochastic Kalman filter, that we assume that the uncertainties are Gaussian. So here the only assumption are related with the bounds. So once we have the formula of the zonotopic Kalman filter, this propagate the centers and P propagate the radius of the zonotope. And from the center and the radius, we can produce at every time instant the adaptive thresholds for the fault detection. So basically, the center is the nominal value of the LPV model, plus minus what is called the interval hull or the box that is calculated using the radius of the zonotope that is propagated using the Riccati equations of the zonotopic Kalman field. So here in the paper, we did also a comparison of this approach that we call ZLPV with the classical methods based on stochastic assumptions. I will not enter in all the discussions that shows why the selection we propose is quite, let's say, appropriate for this application. But basically, one of the main motivations, as I said, it doesn't use the linearization and it doesn't assume anything regarding the noise, only the bounds. So let's move how this approach can be applied for fault detection and isolation in the context of the proposed problem. So here we have a bit the scheme. As I said, the proposed approach is to deal with faults affecting the sensors that are used for estimating the state and are required for the navigation of the autonomous vehicle. In particular, the sensors that we are interested in the fault detection and isolation are the speedometer, odometer, also not named, and the GPS. So for these two sensors, we have a bank of zonotopic observers. One of them is using the speedometer and the other is using the GPS, so that we can know, in the classical manner of the bank of observers, but in this case using the zonotopic scheme, we can know which one of the sensors is in a faulty situation, and then once we know the sensor that is in fault, we can replace estimating with the other. Of course, the quality is not the same. I mean, if the speedometer fails with the GPS, we have more quality, that is the reverse. But at least we can do something. So here we can see the logic behind. So we check first the speedometer. If it is not fault, then we go to the estimation of the state. And in case that there is fault in the GPS or it's fault in the speedometer, we do differently. In fact, if it fails the GPS, even though we can estimate the state, the quality of the estimation is not very good and the company doesn't accept the level of precision. So in this case, the decision is to stop. While if it fails the speedometer, then with the GPS and the zonotopic Kalman filter, we can estimate the rest of the states and we can go on. So here is more or less the logic and the decisions. So to see the results, we were using, or we're doing some tests in the Renault facilities in Spain, as I was commenting at the beginning. This is the case study that was proposed. In fact, the final application that they won is that still will not be commercial, the system, but will be embedded in the vehicles. And when the lorries, no, transporting the new vehicles, they have a parking, and they want that the lorry will let the vehicle in a place at the entrance of the parking, and automatically the vehicle goes and parks in the right place. No? So this is the application that they want at the moment. Maybe in the future they will use for commercial purposes, but in this case the problem was like this. So it was the automatic parking of the vehicles in the parking that they have once the vehicle is finalized and ready for distribution. Of course, this also will allow them to know about the technology of autonomous vehicle and improving the systems that they have. So here we have the map of these Renault facilities where the experiments were done. And the speed is quite low. The maximum is 40, but in general the vehicle moves quite slowly. So for the testing of the solution, there are some scenarios additionally to the normal where we lose some of the sensors because of some reasons, some disconnection. The RTK is the GPS, or some problems with the internet connection. So different faults are considered. So before arriving to the real test, in the scenario of the real parking, we did some testing in simulation. In the plot on the right, in the A, we have a fault affecting, in this case, the speedometer, and we can see that the algorithm detects the fault because the real measurement is outside the bounds of normal behavior predicted by the zonotopic Kalman filter, and on the, let's say, right, we have the same, but with the GPS. So this was the behavior in simulation, and we were also verifying the same scenarios with the real vehicle, obtaining very close results. So as a conclusion, in this paper, we have presented a possible solution. Of course, there are many other possibilities for solving this problem, for the fault detection and isolation, based on monitoring some of the sensors that any autonomous vehicle has, in particular the speedometer and GPS, to detect if those sensors that are very critical, because if we don't have good measurements in these sensors, the safety of the vehicle is not guaranteed. And to do that, we have approached this problem in a non-classical manner. Some of the existing methods assume a statistical distribution of the noise, extended Kalman filters. This is more or less the standard solution. Here, benefiting from this relation that nowadays exists between the extended Kalman filters and the LPV zonotopic observers, we were able to do the same, but without any statistical assumption, only the assumption that the noises and disturbances are unknown but bounded. Also, we have assessed the performance in simulation and in the real experiments. In fact, this is part of a more, let's say, long project where not only we will monitor the safety of the navigation system, that is the problem I'm presenting here, but also the control, the different models that are used in the autonomous vehicle. So that's all. Thank you.
Is there any question?
Thank you, Vicente. Very interesting presentation, and I liked the fact that you have also experimental results. So my question, because these are sensors that are used in many types of vehicles, the speed and the GPS, have you encountered problems with asynchronization of the measurements, and how do you consider this in the decision logic process that you have?
Yes, there are some internal individual. In the vehicle, I didn't enter in these more, let's say, computer-oriented implementations that are required, but yes, there is some algorithms internally that are in charge of what you say, synchronizing the different sensors.
So you don't synchronize the decision
No, there is, could be another way. Yeah, it's a preprocess. Yes, there is a model that is in charge of aligning the information and avoiding, because this is, here I present the solution in case of a fault, but in the normal operation also this is important, because you need to guarantee that all the sensors are providing the information at the right time.
I was wondering regarding your scheduling parameter. It's the angle of the vehicle, like it plays a role, I think, in the scheduling parameters. You have cos and sine of the angle. So you have this linked nonlinearity, and I was wondering, first, if you take uncertainties on this parameter, and secondly, if you take into account in the LPV model these linked nonlinearities, or if you just assume that they are independent of each other. Thank you.
The manner to consider the uncertainties, at least in this particular work, is assuming, as in the classical extended Kalman filter, that the uncertainties is like a disturbance, no, in the modeling. So you, in the calibration phase, no, that you have to calibrate the model in normal behavior, you estimate the error between the model and the data, and you assume that the uncertainty is like an additive term. There are some other works, not in this particular one, where the uncertainty also is considered in the parameters, as you comment, but not in this particular case. Because considering in the matrices, parametric uncertainty creates more trouble in the calculations. It's possible, but it's a little more complex. When the uncertainty is additive, like in the Kalman filters, it's a little more easy in set-based techniques. But could be another way. Could be another way.
Thank you for your presentation. My question was about the different, what is the reasoning behind selecting different actions in case of different sensor faults? So in some cases there was a fault diagnosis, in some cases there was a fallback action like safety stop. So,
in fact, there is a study that is not presented here that they call the hazard and safety analysis, no? Where the company has identified the situations that can occur in the vehicle. And for each situation is a kind of level of criticality. No? And if you cannot guarantee, for example, the precision, no, inside the range, the best that you can do is a stop. No? So for every particular situation, there is a decision that is analyzed by the experts of safety of the company that decides what to do. Maybe, of course, this in the future can change, no? Because the technology evolves. No? But the decision of what to do depends on the level of safety that you can provide and the quality of the results you can produce. With the quality of estimations that we can produce with the GPS, we can continue, but in the case of the speedometer, the precision was so high that they don't want to risk.
Thank you. Thank you again to the speaker. Now we have the videos. So the fourth paper has a video presentation.
My name is and today I am pleased to share our research on enhancing fault diagnosis of inserting grid-connected PV systems using deep-gated recurrent units-based Bayesian optimization. To guide you through our work, I have structured the presentation as follows. I will begin with an overview of the necessity of renewable energy emphasizing PV source. I will discuss the susceptibility of these systems to failures. Next, I will outline the primary objective of our research. Following this, I will introduce our approach. Then I will describe the specific grid-connected PV system and the fault scenario addressed and discuss the performance improvement of our methodology. Finally, I will summarize the key findings and implications of our research. Over the last years, the world has witnessed a drastic increase in terms of using renewable energy, which is considered a reliable way of achieving the world's climatic targets by reducing carbon dioxide emissions caused by the huge consumption of coal, oil, and fossil fuels. Among these sources, photovoltaic energy is categorized as one of the most essentially substitute energy due to the efficiency of electricity cost and technological maturity. Accordingly, these systems may be susceptible to various faults, generating deterioration or total collapse of this operating system, which results in extended downtime maintenance period. Therefore, early fault detection and diagnosis are an efficient procedure to improve the operation of these systems. Recently, the FDG has drawn attention to many research studies. Generally, fault detection and diagnosis approach can be categorized into two main classes, the model-based and the data-driven based methods as illustrated in this flowchart. Model-based fault detection and diagnosis use observers and system identification models of the processes. It demands precise mathematical model, which is complicated to acquire in reality. Actually, its performance is dramatically impacted in front of uncertainties and unmodeled noises. While the data-driven methods aims to extract information from the measured signals to train the model and then be used for the diagnosis in the testing phase. They are well appropriate for complicated systems where they are hard to determine the precise model. Currently, the smart industry is boosting and the data can be gathered considerably more rapidly than at any other time. This offers opportunity for the data-driven basic FGT approaches to overuse the massive data and has obtained increasing attention from the researchers and engineers. Given the advantages of data-driven methods in using large datasets, our approach focuses on enhancing fault diagnosis for photovoltaic systems through a deep learning model combined with Bayesian optimization as illustrated in this figure. Specifically, we utilize a deep-gated recurrent unit network to analyze time series data from grid-connected photovoltaic systems, which is particularly dedicated at capturing comfort dependency and handling noisy inputs. To optimize further the performance of this model, we employ Bayesian optimization, which efficiently searches the hyperparameter space to identify the best configuration for robust and accurate fault diagnosis. After that, the network is expanded to interval representation in order to handle uncertainties effectively. And before delving further into our approach, let's take a moment to examine each technique individually. Actually, the measured process data in real-life situations are uncertain. These uncertainties have unfavorable effects on the determining model and so on the FDT achievement. The uncertainties in the system is the consideration of minimum and maximum values, while the representation of single-valued data is achieved by simplifying the data over the mining procedure. Thus, the interval value data representation offers a better overview on the measured phenomenon compared to the single values representation. Besides, inaccuracy, uncertainty, or parameter variability might categorize the important information describing the real system. Thus, classical data is not able to present these dissimilarities, and for this reason it is important to represent the data as interval valued. The following equations denote the interval data representation. Moving on the next slide, we will delve into the principles of the gated recurrent unit and its application with interval valued data. The gated recurrent unit is a type of recurrent neural network architecture designed to effectively capture and utilize long dependency in sequential data. It consists of gating mechanisms that regulate the flow of information within the network. Unlike traditional RNN, this unit has fewer parameters. They feature an update and a reset gate as illustrated in this figure, which control how much information from previous timestamps should be retained or discarded. This allows this unit to overcome the vanishing gradient problem and better model long-range dependency in sequential data. The following equations define the basic mechanism of gated recurrent units and how it incorporates the interval data representation to enhance its performance in handling uncertainties. Furthermore, to ensure that our model operates at its optimal capacity, we use Bayesian optimization. This technique efficiently navigates the hyperparameter space, identifying the best configuration that enhance the models for diagnosis accuracy. In fact, this technique involves several steps. It constructs a surrogate model to approximate the model performance as a function of hyperparameters, then uses an acquisition function to balance exploration and exploitation in selecting the next hyperparameters to evaluate. After that, it evaluates the model with the chosen hyperparameters, records performance, and updates the surrogate model. And finally, it repeats the process until a stopping criterion is met. By combining the advantages of the proposed network in handling sequential data with the precision of Bayesian optimization, our approach aims to significantly improve the fault diagnosis capability of grid-connected PV systems, making them more reliable and resilient to data imperfection. Having discussed our proposed approach and the techniques we use, let's now shift our focus to the studied system that provides the foundation for our research. In this study, datasets sourced from a grid-connected photovoltaic system emulator are used. The PV array emulator and grid emulator serve as substitute for actual photovoltaic arrays and grids, allowing the introduction of diverse faults into these pivotal components of grid-connected photovoltaic system. Moreover, these emulators provide the flexibility to control and manipulate various system parameters and outdoor conditions such as temperature, irradiance, and humidity settings. This table provides more comprehensive information and specific details regarding the measurements comprising 9 representative variables. Now that we have an understanding of the studied system, let's delve into the different faults we addressed in our research. The emulators allow us to introduce a variety of faults into the grid-connected photovoltaic system, which can be categorized into PV side faults like sensor faults, PV panel faults, and PV panel connection faults. Also, grid side faults such as inverter fault and grid connection faults. Moving on to our experimental setup for fault detection and diagnosis, we execute a series of experiments that involves the collection and recording of experimental data variables as shared in this table. The healthy state of the grid-connected photovoltaic system is denoted as class 0, while the remaining 5 operating models are categorized as classes 1 to 5. Detailed description for each operating condition along with the corresponding number of samples are provided in this table. Now, let's examine the results obtained from our approach. The first table provides a comprehensive summary of the results obtained through the presented approach using both single value and interval value representation in the testing phase. The results demonstrate that the proposed technique achieve high performance across all utilized classification metrics, including accuracy, recall, precision, and computation time, reaching accuracy rates of 99.92% and 95.78%. In this study, the hyperparameters established through testing iteration are considered the best ones, since part iteration didn't devise significant change. The tuned hyperparameter values of the proposed model are illustrated in the second table. To better evaluate the proposed techniques and calculate the recall and precision metrics, the results obtained are summarized in these figures through the confusion matrices during the testing phase. Actually, the confusion matrix serves as a valuable visualization tool, enabling us to assess how well predicted classes align with each one. We can recap our main points in these conclusions. In this study, an affordable program framework is proposed for detecting and diagnosing faults in grid-connected photovoltaic systems. The proposed methodology enhances the performance of the gated reference unit model by fine-tuning its hyperparameters through the Bayesian optimization algorithm. Also, an interval value error, noise, and parameters variability within the read connected to voltage system, which are introduced based on the application of interval value datasets. The experimental results underscore the robustness and high performance attributes for the proposed for diagnostic paradigms, validating their efficacy in real-world application under complexities. Thanks for your time and attention.
Presentation.
fifth paper, fourth presentation for today. This is also a video presentation.
Good afternoon, everyone. My name is Daikun Chang from the University of Aeronautics and Astronautics. Today, I'm going to present our research on adaptive fault-tolerant tracking control for multiple inputs, multiple output linear systems with time-varying or state constraints. I will present the main concepts of this report from the following 6 aspects: introduction, proper formulation, state transformation, concentrated control design, stability analysis, and the last part is the simulation results. Let's first look at the first part, the introduction. In this program, we focus on multivariables, profit-based nonlinear systems. Those systems present unique challenges due to their complex nature, including time-varying for state constraints. Those constraints can be constant or time-varying, asymmetric, and apply to the entire state space. Moreover, those systems are characterized by either linear functions and uncertainties, so it's necessary to design robust fault-tolerant tracking control mechanisms. So far, many control methods has been developed to handle such systems, include dynamic inverting control, model productive control, sliding mode control, backslapping control, and adaptive control. For handling constraints, techniques like variable Lyapunov functions, integral variable Lyapunov functions, and nonlinear mapping are employed. Those methods help ensure that the system operates within safe and predefined boundaries. Our research addressed several key challenges: mechanism time-varying for state constraints, controlling multivariable profit-based linear systems, improvement for tolerant tracking control to handle uncertainties and potential competent faults. And our contributions to this field are significant, including novel fault-tolerant tracking control algorithm is designed. The second one is the variability constructions are eliminated by contracting state mapping. And the third is the neural networks and adaptive techniques are applied. The second part is the problem formulation. Consider multiple inputs, multiple output profit-based linear systems represented by the equation 2 and 1. The goals are to design a controller such that the desired output widely can be tracked. And the second one is the state variables satisfy time margin for state constraints. This means that the system must follow the desired trajectory while adhering to satisfy the operational constraints at all times. To model actual faults, we use the following receptions: 2 and 3. Before performing state transitions and designing controllers, we make several key assumptions. The first one is that the design output YB and its derivatives are bounded and continuous. The second one is there exists small positive constraints ensure the constraints are met. And the second one is the act fault is bounded. The third part is the state transformation. To handle state constraints, we construct functions that depict the distance between the states and the constraint boundaries, as shown in equation 3 and 1, and the equation 3 and 2. Next, we design transformation functions 3 and 3. to convert the constraint system into an unconstrained one. Therefore, we can get the unconstrained system shown in equation 3 and 5. This transformation supplies simple physics the control design process by allowing us to apply standard control techniques to the transformed system. The fourth part is the constraint controller design. Before designing the controller, we define error transformations to facilitate the controller design at equation 3 and as equation 4 and 1. Those transformations help us focus on the tracking error, making it easier to develop effective control schemes. The adaptive controller is designed in several steps, starting with multiple controllers and adaptive update laws, as shown in equations 4 and 4 to equations 4 and 6. This approach allows the controller to adapt to changes and uncertainties in real time, ensuring robust performance even in the presence of faults. The fifth part is the stability analysis. Section 1 states that if the controller laws and the adaptive update laws are plotted, the closed-loop system remains stable. All signals are bounded and tracking errors remain within acceptable limits. Furthermore, time-varying states constraints are satisfied, ensuring the system operates safely and effectively. The sixth part is the simulation result. We dictate our approach using a multiple input and multiple output Lagrange robotic systems. The simulation results demonstrate that the effectiveness of our control schemes in maintaining desired transitions and adhering to state constraints despite actor force. Next, let us see the simulation result. Finger 1 and Finger 2 shows the tracking performance of the system, indicating how well the desired trigger race is followed. Fingers 3 and 4 shows the response of the attitude angular rate from those fingers. It can be seen that the controller designs in this paper stabilizes the attitude angular rate state. Finger 5 depicts tracking errors over time, illustrating the controller's actually. Finger 6 shows the controller input signals, reflecting the controller's actions to achieve desired performance. In this program, we have developed a novel adaptive tolerant tracking control method for multiple input, multiple output linear systems with time-varying state constraints. Approach effectively address the challenges posed by those systems and demonstrate promising results in simulations. This research proves the way for more robust and reliable control schemes in practical applications. That's all. Thank you for your attention.
come back from configuration.
Yes.
Perfect. Try to. No, there is no. Okay. Oh, here. You can take this.
Okay.
And if you want to point something better with this,
yes.
And to talk, try to approach to the microphone.
Okay.
For people attending online can.
Okay. Thank you. Can I start?
One. Okay, so let me start introducing. You are now Davide Cesani. Yes. Next speaker is Davide Cesani. He's from the University of Bergamo, no? I guess. And the title of the talk is The Scenario Approach for Data-Driven Prognostics. So, when you want.
Good afternoon, everyone. So this presentation, I show you a scenario approach for data-driven prognostic methods. So I will start with a brief introduction of data-driven prognostic under uncertainty, then the scenario approach, the theory behind the method, so the method itself, the results, and the conclusion. So let's start with a brief introduction of data-driven prognostic under uncertainty. So prognostics is the process of forecasting the time to failure of an industrial item using degradation model. The classical data-driven prognostic framework starts from raw sensor data, then extract condition indicators or degradation models, and then perform a RAL estimation. But we are in the presence of uncertainty on data acquisition. So let's propagate this uncertainty on condition indicators and then on RAL estimation. Using a lot of data, we can manage this uncertainty, but data in the context of prognostics are run-to-failure experiments that are costly and difficult to implement in industry. So this work aims to propose a data-driven prognostic method that considers only a single run-to-failure experiment and manage the uncertainty using the scenario approach theory, in particular the interval predictor method. So the theory behind the method consider n independent observation called the scenarios, no matter what G is form or the noise is form, so we are no assumption on the noise. The interval predictor method, we assume for simplicity a standard regression model of G at a polynomial model of degree n, and then we resolve this optimization problem in a epigraphical form. So we have an auxiliary variable in the constraint. So this optimization problem is convex, so the solution are the global optimal. So with the V star, the optimal parameter of the polynomial model, we define the polynomial epsilon at, y at, and then with the L star, we form the prediction interval, a lawyer, so with upper bound y at plus L and lower bound y at minus L. In a figure, we obtain something like that, with the interval that is centered in y at. So given a new scenario, so a new data from the same data generator model, the probability that the new scenario lies outside this interval is the violation, it is this probability. The scenario theory, the main theorem of the scenario theory, says that for any risk parameter epsilon in 0,1, for example 5% or 0.05, and for any confidence parameter beta in 0,1, that is a very small parameter, for example 10 at the power of minus 9, then if the number of scenarios is greater or equal this quantity that depends from the risk parameter, the confidence parameter, and the complexity of the polynomial on the center of the interval, with the probability 1 minus beta, the lawyer fails to correctly predict the new scenario with probability no more than epsilon. So we have an upper bound on the probability of fails, of the prediction fails of this lawyer. So, but if the regression model that we assume is too simple, the interval predictor method still works. So we have a larger interval, but the method it works. So the method itself is a two-step algorithm. The first step is done only once. Is done on the only one run to failure that we are available. Is made offline and allowed us to define the prognostic and operative threshold that we use in step 2. Step 2 is the online part of the method that use the primary lawyer or if necessary, update it. Let's start with the first step. So the data acquisition are simple. We given a component A, for example, a bearing, we perform a run to failure experiment on this, only one run to failure experiment on this component. And then we, on the raw data, we define the degradation threshold where the items start to degrade. When it is degraded, the red one, and the black one is when the item breaks down. Then, from the raw data, we extract with some mathematical steps, dividing the data in n batches and perform the standard deviation on each batch. The cumulative, we obtain the cumulative condition indicator that we allow to have a sort of a degradation model of our items. We are interested in the time to alarm, so we focus on alarm threshold when the item is critically degraded to allow better maintenance and easier maintenance. The scenario in this context is the couple time and degradation point at the time. So the primary lawyer creation solve the optimization problem, is convex, and obtain a lawyer like this. If we zoom in this part, we can clearly see that the blue line, the blue dotted line, is the true degradation of the component, is inside the lawyer, and then we can make with the light blue dashed line prediction on the real time to alarm. This obviously in this lawyer has the probability as the property gives by the main theorem of the scenario approach. The last part of step 1 is defining the threshold T1 and T2 that are two operative thresholds that we use in step 2 to use properly this primary lawyer. So the step 2 is the only makes online runtime in this case. I can show you only data when the data acquisition is completed, but you have to imagine that we work on data batch of that cover x seconds of raw acquisition. Of each second of acquisition, we create the cumulative condition indicator to obtain something similar to previous, where we are interested in the time to alarm, where the condition indicator touches the alarm threshold. All the thresholds and the time instance are defined in step 1. So the main idea is that given a component B of the same family of component A, using previously to define the primary lawyer, the degradation of component B can be similar to degradation A, or can be different to degradation of primary component. So, in the first case, when degradation of component B is similar to degradation of component A, so we can say that between the two operative thresholds, T1 and T2, the degradation, the yellow line in this plot, lies outside the primary lawyer for a limited number of points. We can assume that the degradation of B we assume that the degradation of B is equal to the degradation of A. So we don't need to create a new lawyer. We just use the primary lawyer to provide rule estimation. In this zoomed part, you can see that with the light blue dashed line, we are so close to the real time to alarm of the yellow curves. So we can use the same lawyer, no further lawyer computation are needed, and a human operator can check every time and having an idea of the degradation of all items. So, in the other case, if degradation B is different to degradation of A, so we have the degradation B outside the primary lawyer for a large number of points, we need to compute another lawyer. So, a new lawyer is needed, and when we perform the new computation only when the condition indicator, the solid line in this zoomed part, touches the purple threshold, the TGK, that is an operative threshold. You can see that the real data lies outside also the new lawyer. So this is because we know data only until this time. So these data are unknown at the time of the computation. Consequently, we need to fine-tune the lawyer. We acquire new sum data from this yellow point to this yellow point, and we perform another computation. You can see that the prediction come closer to the real time to alarm. For all the lawyer, obviously, the main theory machinery approach still holds. So we applied this idea on the Pronostia bearings dataset that is available online. We use the longest proof to the primary lawyer creation, so to start to the step one of our methods, and the other two to validate the methods in substance. So they are the same imaging of before. So in one case, the degradation is similar to the primary lawyer. We use, for simplicity, a polynomial of order 6, a risk parameter fixed to 5%, and confidence beta fixed to 10 at the power of minus 9. In the yellow case, we don't need any computation, additional computation. In the purple one, instead, we need both a new computation and then a fine-tuning computation. You know, in words, what about the width of this interval? So the primary lawyers is 20 minutes width, that on data acquire more than 6-hour test is an acceptable width. In the case of additional computation, the width of the lawyers drops down to 2 minutes and 30 seconds. So we can do a forecasting of the time to alarm with this time interval. The last things that we did is to compare the RAL error, so the actual RAL minus the predicted RAL, with a summation wavelet extreme learning machine. And we can say that in 3 different cases. We can say that in the blue case, our method fails. Our method errors is only 30 seconds on 6-hour test, 13 minutes in the green line, and 50 minutes in the red one. The red ones, you can see that the model updates decrease in a large way the error committed by the models. Conclusion, a little bit recap of this presentation. So our method uses only one run to failure. It creates a primary lawyer as an oracle that when you have other components, you compare with this oracle and you can understand if you can assume the degradation are similar or not similar. And the scenario theory allows us to manage the uncertainty and gives probability guarantees on the estimation we do. Thank you.
I mean, in the application that you show is this rolling beers, no? Yes. And the degradation is only, I mean, physical, or there is some, you take into account that you apply some action?
Oh, no, Prognosta Bearings is a platform that accelerates the degradation of bearings. So it's only physical
degradation.
Physical degradation, yes.
And it's question of time.
Yeah.
So there is no
it's
more.
It's only a question of time with accelerometers. We get data.
No, because another interesting, we were working also in the past, extension of this is to use these interval predictors, for example, for modeling the residuals degradation. No?
Yeah.
And you can use also the same idea for prognostics further than physical only degradation.
Yes.
It's another idea. Some additional questions, comments? Yes.
Thank you for the presentation. About the degradation model, is this a standard model? Is that something that you designed, you selected? This sigma tilde?
We selected from the literature.
Okay.
It's a condition indicator that we select from the literature, and we use to create this condition indicator. Is qua. We select from this paper, and we apply it to have a monotonic condition indicator to perform prognostics.
Okay, thank you.
Some additional comments, questions? No? So thank you again for the talk. And thank you everybody for attending the session. Now is coffee break, but also there are plenty of new sessions to attend after that. Okay, see you.
here? Yeah, on stage. Or maybe you should come here and I'll come here. Because we're doing the second one.
That's okay.
So, try to control this.
Hello, good afternoon. So this is the last session for today, and this is a different type of a session, a round table on gnosis for maintenance, from diagnosis to prognosis and health-aware control. Okay, I will start with the word gnosis, which is a Greek word, gnosis, and means knowledge. Okay, and that's why it's the second part of diagnosis and prognosis. So here we'll see today how we are using knowledge, gnosis, for doing diagnosis, but the main goal is the maintenance, and the panelists will talk about it. A bit briefly about the motivation for this round table. I'm working on the fault diagnosis and fault tolerant control over the last 15 years, let's say. And in collaboration, when I discuss with industrial partners especially, and I'm talking about fault diagnosis and fault tolerant control and detection and reconfiguration, usually the discussion changes to what can you do about maintenance? Can we use the outcome of what we are doing for maintenance? Can we make maintenance automatic? This is a golden question. Can we automatize the maintenance process? How can we do better? So I thought that it's time our community to discuss about this integration of fault diagnosis and the fault tolerant control that we present here, very nice techniques, and how we can match with maintenance and prognosis, a word that at least in the Netherlands our industrial partners are not very familiar, the prognosis. In this panel. And I contacted one of the experts, Didier Teyol, which is not here today, but he put in contact also with Mayank Ja, correct? Okay. Yeah, we are here. I had the pleasure to collaborate with them and organize this panel. And besides Mayank, who is the organizer, and we'll talk about a bit, and the panelists, we have 3 more panelists here. So it's Vicent Puig, full professor from Technical University of Catalonia, Jing Jiang, full professor from University of Western Ontario, and my colleague Alfredo Nunes from Delft University, associate professor from Delft University of Technology. So Mayank, would you like to?
Yeah, thanks Vasu, and it's really a pleasure to co-organize this session with you. And Didier could not be here with us, also a pleasure to be part of the panelists.
Just before this. So, we have given a bit of structure in order to engage you more, so you will hear the experts, but we are going to pose some questions to you, and you can ask questions to the panelists and have a discussion. This is the main point, that we have a discussion. So, in order to have a smooth discussion, I will be the chair, but also Nikos Kouliatsos, my PhD student, will be the co-chair, and we will facilitate this discussion, okay? So, yes?
I think we need to also explain the functioning of Mentimeter.
I would say, in the first question, I will explain, okay? Not spend time on this. I will give the floor to Alfredo Nunes and present his work. Very short presentation about the topic before the discussion. You can use, yes, Alfredo, please use this.
That way also.
Yeah. Yes. And you can use the mouse for changing. Could you please put it in presentation mode? Yes, perfect. Thank you.
Perfect. So thank you so much for having me here today. A pleasure to come here to Ferrara to talk about railway systems. That is my passion. So as I was introduced, I'm an associate professor at the Delft University of Technology. I work in the section of railway engineering, and my research field is called intelligent railway infrastructure. So somehow I try to capture the inherent intelligence that somehow the infrastructure is showing to us, in despite that it's not a living being. Part of the motivation, you heard that? That one is more common, but the first noise was actually the defect that you see here on top is called short pitch corrugation. Maybe we could have been in the opera, and then the corrugation could have said this very high pitch voice, but it sounds interesting. But if you live in the surroundings of this, every train passing by, oh, super annoying. So somehow the railways, they try to talk to us. We need then the sensors, the technologies to try to understand what they're trying to say. Also, when we treat, and this is in relation to maintenance, when we treat them good, then the problems that disappear, they don't appear again. But when you don't do it correctly, every time and then, same defect, same place, same location. Then we said also that the rail has a memory of an elephant. So then it will remember always where the problems are. Of course, we know this is not a biological intelligence, but somehow it's a behavior that can resemble it. As for the, maybe I just skip one. Okay. As for the importance of the railway infrastructure at European level, this is one of the key infrastructures. So there's a major shift for moving passengers and freight from road to rail, and there's major investments in research as well. Currently, I'm working in this project, I Am for Rail, that is one of the largest projects on asset management for railway infrastructure. And here we have the key players of the railway industry, all of them working for new solutions. If you're not familiar with the Netherlands, this is how it looks like the railway infrastructure in a normal day. It's one of the most densely used railways networks. You can imagine if any problem happens somewhere here, it will affect a lot of trains. But new technologies, the ones that you are all working on, intelligent vehicles, they are all now making possible to include new sensor technologies on the vehicles, in the vehicles. So now, later, while this is currently a problem, such a dense network, now each of those trains can collect information about infrastructure on the run. So then maybe if there's one area in Amsterdam that we want to have additional monitoring, okay, we activate the trains that are passing by, they can take the pictures, the vibrations, the laser, the whatever you want, and then you can get almost online 24/7 updates. So then somehow we have an intelligent network. At the TU Delft, we have a measurement train. So we conduct the research mostly on trying to do as much as possible on the run, because basically we don't have time for maintenance or monitoring. So this is our train. Some of the technologies that we test, acceleration signals, so that then whenever a wheel, let's say, is passing over a defect, just like when you drive, here in the railways, the same. The difference is metal to metal contact. Then you really feel then with the very small defect, because very fast you feel it. So that's what we try to do, to detect local defects, local changes on the run. So this is one of the technologies we've been working on. The methodology then also almost real time. When I started working in this field, it took us weeks to process this kind of data. It was 25.6 hertz, kilohertz of measurement. Now this is almost in real time. We did some measurement campaigns in the iron ore line in Sweden, 400 kilometers of railway, and then we basically monitor it almost in real time. So all of this to extract knowledge about infrastructure. We also have the connection with laboratory tests. Then here some the temperature effects for the growing of defects. And one of the technologies that we've been working on is on the monitoring of dynamic parameters. For instance, you are all familiar with a spring. The spring has a stiffness value. However, in the railways, depends on the frequency that the stiffness will change. So what we try to do then is to measure functions, models, while on the run. For this, we need two things, input and output. We use the input, the excitation of the train. That's the vibration that we collect with accelerometers. We use as output the technology of laser Doppler vibrometer. Basically, we measure the speed, and then we point it to the locations where we want to estimate the variations. So for instance here, this is the pointer over here. Then no matter the speed, we collect also information from the ballast, sleeper, doesn't matter. We get the transfer functions, every local and every position, we get dynamic parameters. We claim that these dynamic parameters, instead of one single value, now we get a function, gives much more information. But how can we make it use for this, for maintenance? Because then basically now we are making things more complex. They're already complex enough. Railways is distributed parameter system. Different behavior at different locations, different time. So, and now we have functions that keep changing over time. Let's see how we manage to sell this idea. Thank you so much.
Okay, thank you, Alfredo. Okay, so now we have a question. We are going to use the Medimeter. I don't know if you are familiar, just to see some interesting aspects of this. So you see there is a QR code. You can use the QR code, or either you can connect with medi.com and use the number there. I think QR code is easier. And there is the question, what are the most used structural monitoring methods for railway maintenance? So we used ChatGPT, the tool that our students are using. When you are asking, could you find a method? And we got some answers. One was using human operators, but we exclude this. And there are these methods. So are you familiar with this? I mean, we had also, Alfredo talked about it. Yeah, it would be good to see alternatives. What are the different methods for structural monitoring? And we see that we have, there is the winner, but what do you think, Alfredo?
Well, actually, the answer, the first one is quite correct.
Okay.
Most of the
they are not wrong.
No, but actually the option you said that is based on human observations, that's actually the more commonly used, because there are a lot of railway lines that they don't have the equipment. And we do have sometimes this measurement coach that we run them like once or twice per year. But then it opens the question, how can we estimate what's going on in between of those measurement campaigns? They're quite accurate. The more traditional one actually is track geometry. I didn't talk that much about it, but it basically is the static, let's say, alignment of the rails. So how far away they are from each other. So that's and we call it the static version. It's important. But with the dynamics, you see really in operation what's going on. So for instance, we have a problem in a project in Romania. The location with more energy, with more problems, was a place that the geometry was fine. But then when the train passed over, you could feel and see the vibration of the sleeper moving, shaking very terribly. That is something that was not detected by the static measurement, but the dynamic. So this vibration base is not yet fully in the standards. So it's part of the research. The third one.
Okay, you know better, you have a vision on this. Okay, vibration monitoring.
So, and the work now is towards to make this a standard because it's so useful, but then it still is very complex because then you have to explain what is a response, frequency response. While the static measurement, you know, okay, it's a millimeter, it's a value. So, and also the vibrations, they depend on the speed of the trains. And the trains, they go at any speed sometimes. They're braking, accelerating. And then at every speed and every location, you have a dynamic response. So, and the system that also depends on the loading. You have the iron ore, 31 tons. A passenger train different. The excitation is different. Then it's a very nonlinear problem.
Okay, thank you.
Good responses.
Okay. Are there any questions from the audience? that you would like to ask Alfredo, for example, for this topic. We can continue the discussion, but our questions...
Consider a breach, because in the condition when there is a breach, there's a long problem with the breach, because they have vibration breach, and again the train. When there are wind.
Exactly, exactly. So, and it's the failure mechanisms come from the usage, but also, for instance, the environmental pressure, the wind, a lot of effects. And actually, at the breach, you have a transition. You go from an area that you have soil to some that then you don't have anymore. All of those transitions, the infrastructures, they feel it. They don't like it. And then they degrade faster. That means that bridges that they have a special attention for the railways. And those are the locations where most problems happen when you have a transition. Yes.
Okay, thank you.
Can I ask a question?
Yes, yes, of course, but that's, we have to discuss.
Right. The question I have is, has fiber optic sensors been used for the train track monitoring? Because it seems to be a natural application. Yes. Yeah. Can you comment on that?
Yes, so the thing is then there are also a lot of these cables that are already existing there. And then it gives the information from the track side. For instance, we have been using it for detecting trespassers. So people walking in the track, but also you can see the trains passing by, the vibrations, and you can get a lot of much more information track side. To me, there are a lot of new techniques. They all have their pros and cons. When we find the way that they all work together, then we get better, more, let's say, holistic responses of what's going on. More, let's say, we see the problem for different perspectives. And then I think it enriches the decision-making, particularly for maintenance. But then it's not anymore the decision of do it or not, but you give the information. Like, okay, the fiber optics are indicating that there's something going on there. The vibration signal, the static, all the information then lets you into analyzing not just the problem, but maybe the root cause as well. Then when you know the cause of the problems, maybe you can then not just replace that part, but also the whole network. Or to also teach to other infra managers to also improve their policies. So how can they also improve and prevent problems that are occurring in other networks?
Okay, thank you. Yeah, Maya. That's a good question. So keeping in the spirit of the topic of today's roundtable, from diagnosis to prognosis, how easy or difficult it is to prognose the problem. I believe a lot of work exists on the diagnosis front using vibration analysis, but is it easy to also follow the evolution of the fault in your context, or how difficult it is?
It's rather challenging because we have a spare measurement, let's say, like once or twice per year. But then there's also an additional challenge, for instance, in the Netherlands, that we have contractors. So then the companies, they make business by creating their own policies. But then at the end, they get measured by a certain level of compliance from the standards. Then there is a lot of know-how in the industry. But it also is related to also how the companies, they will make money. So it's also about a lot of private information. So, but apart of that, the sensing technology nowadays, they allow almost a daily monitoring system. So actually, with the technologies today now, it's simple to have a better track and the evolution of the defects. And one part that is interesting in railways is that we have a combination, it's a multi-rate system. So we have very slow dynamics.
Multi-rate?
Multi-rate. Okay. So very slow dynamics. So some defects, since they are little till they crack, 2 years. But there are other defects that then when the crack is faster, then the rail break could be in a few days, in an hour. So then you really need the monitoring to be quite frequent, actually.
Okay, thank you. I have a question regarding how you use the information. You know that there is a crack, okay? I guess that the maintenance is not immediate. It depends on the length. But can you indicate, let's say, to the trains that, look, you can go up to this speed in order to, let's say, to prolong the time and to delay the maintenance? So to have like a feedback to the network and how we operate the network.
Now you ask a question in the spirit of health-aware control.
Yes, that's why I'm asking the question. So to put a bit of control indirectly, like, reach that speed up to that point in order to make more sustainable, to have, to increase the...
So the implementation that I have seen in the Netherlands for the high-speed line is basically a lookup table. So one of the most simple control strategies. So you see the cases. If this situation is happening, then you don't need a speed reduction, for instance. But when the sensor indicates there's a crack that is deep enough, you then can start increasing the speed limit. Basically, in the railways, then of course we prefer to not have rail brakes, but then but you can still operate under very low speed. But then, okay, why do you have a train passing by if you can walk faster than the train, you know? So you don't want the low speed there. But indeed, so there is these techniques that are quite tailored to cases, so like 5 cases. But then, we might be too conservative. Maybe then, if for instance the crack it has also errors in the prediction. So maybe we are reducing the speed more than needed, but then we start playing with safety. And then, you have a lot of people going there in those huge machines. So, but the technique available now, basically, lookup tables.
Okay.
Make a comment. I think this is exactly what the difference between the academic and the industry. So our operators, for example, train engineers or the maintenance crews, they have to follow certain regulations, right? And if you see a crack, and you said, okay, it's small. Okay, let's go. Something happens, you go to jail. And if there's the tables and you follow the rules, if there's a crack of a certain size, even though it may be safe to pass by, but you got to stop the train. So there is strict regulations, and when you become engineer, you have to pass the exams. So this is where difference between the academic and the industry.
Okay, and at least in the Netherlands, I know that we have ProRail responsible for the network, the railway network, but there is NS, which are responsible for the rolling stocks. So is there, let's say, a communication between the vehicle operator and the network operator about the maintenance? I mean, to improve the maintenance, let's say, because you mentioned that there are trains with sensors, correct?
Yes.
They provide the data to the railway operator to do maintenance. Do they provide to you data?
Yes. So indeed, the data collected by the trains will belong, let's say, to the railway undertaker. So for instance, NS is one of them. There are also other operators in the network. And then they have their special communication, because in the past there used to be one single company. So then you could call the colleague if the train is destroying the catenary system. You could just say, oh, this train is making a mess, so stop it. Then it was in this period of privatization that then privatizing was sexy. Then they did the separation between the wheel and track. Then we have 2 different companies. And during a period of some years, they had to adjust into this decoupling. And then it took a while to learn. And then there was a drop in performance. There was, in general, people were not happy about the performance of the railway in that time. But today, in spite of that dark period, it allowed to create railway companies. And then there's an industry now that is going on, that is having a lot of expertise, a lot of know-how, and then very well connected. So indeed, the railways is a whole system by itself, not just the railways itself, but also the external part. So the railway is one of the companies that have the most neighbors. Then you don't like a noisy neighbor. So there are a lot of interfaces, all of them super challenging. The train and track is one of the important ones, because actually the defects, if you have a defect in the wheel, and then you can propagate it every 2.6 meters, one defect in the rail. So then, there are those procedures nowadays in place and some communication, and it's important for the whole system performance.
Yeah, maybe one question for me. Maybe you mentioned it, but it was not clear. Like, returning to the Mentimeter and those three methods for structural monitoring, I was wondering whether there are any merits in combining different methods, or is it just we pick one of those methods?
To me, the sense in principle, the physics behind it is quite different in the three cases. Current technologies, for instance, for detecting the cracks, we use ultrasonic and also eddy current. Some of them, they have a capacity of depth, of how accurate they are, but still in that field, the results that we get are quite aggregate. It's difficult then to detect one crack and then to go to the field and to find it. So it's quite aggregate, but it is important information. The other part, for instance, the vibration, collects the whole response of the whole system, not just the rail when it's the crack, but also the effect of the slipper and all the sublayers. So it's like a more, let's say, a total response, total energy.
In that respect, if I may, so between the vibration monitoring and ultrasonic testing, given this, as you say, you capture whole vibrations from parasitic elements. Which one do you prefer? Which one turns out to be more efficient?
Or you may say an alternative effort method.
One question. Do you make something when there is an event like an earthquake? Because I know that in Japan, they especially after an earthquake, they check everything.
Yes.
Every kilometer is checked in Japan and in Chile as well.
In Chile, yeah. I'm from Chile.
Of course, as well. In the countries where Italy, you have as well a lot of earthquakes, and I think that because you have a specific vibration as well.
Exactly, and actually you can detect it and.
To test more and to say exactly the conditions, how the stiffness and all this thing change.
Exactly. So here, the other time we were talking about all of these effects, let's say. So we have the crack that is quite local, a few millimeters. We have also the major event that could destroy the whole infrastructure. And then it's all about, of course, the early detection, the techniques, for instance, for the earthquake, to know, okay, once it's generated, sometimes you have the time to stop the operations.
They do it in Japan.
In Japan, they do it.
They
Yeah.
have some places where it's more safety. And then when there is an earthquake, the operator knows that they have to stop it.
Exactly. So that's during the disaster, let's say, but there's also measures that you do pre-disaster, that is by increasing the resilience. So the design, the embankment, that is able to capture those vibrations, let's say, and to dissipate them. So you have a lot of actions, actually, from design. Those are mostly on the root cause of the problems. But then you have, in the case of the ultrasonic, that if you measure the cracks and they're little enough, you can then do grinding. Grinding is to remove a thin layer of the top of the rail. So with the stones, like when you also kill your dead skins. So similarly with the rail, you clean the rail, and if the cracks are small enough, the problem disappears forever. But if there's a crack that is deep and you do the grinding, the crack remains. And actually then it accelerates later the growth of the defect. So you have to be careful. And then each information that provides the particular picture, but the holistic response, maintenance, all connected, they have to be very specific.
Okay. Thank you very much, Alfredo. We are going to move a bit. We saw here a very nice application and very important in everyday life, railway. But we are going to continue, we change with the presentation of Jing Mayang. Thank you. So Jing Jiang is going to discuss about applications, again, industrial systems, and is about how to apply fault-tolerant control outcome, the information of fault-tolerant control for maintenance. And we will see nice, interesting industrial systems, okay? And then we will initiate the discussion. 5 minutes of presentation, and then we start the discussion.
Okay. So I have been doing the fault detection diagnostic and fault tolerant control for a long time. And then in the last about 20 years, I got involved with some real industry process, in particular looking at instrumentation control for inside a nuclear power plant, which is a very safety critical system. Then when I talk to industry, look at the industries, all of a sudden I realize there's a huge difference between academic, what we talk about, the terminology we use, and what the industry is using. So I wanted to use this opportunity to share some of my observations and to see how we can work together to use some from academic point of view, how can we help to industry solve their problem, and in the meantime we want to make sure that what we're working on is relevant to industry. And so in other words, they say, well, if we assume it's a fault-tolerant control, which is the fault occurred in the actuator, in the sensors, in the process, how do we translate this diagram from the left to a more complicated system to the right? So I'm just going to right to the problem. In academic perspective, I think most of us here are professors, students, researchers, and we make a lot of assumptions when we present the paper. Assume that the system is represented by particular models, and certain fault occurs. With certain fault occurs, some parameter changes. But what does this really mean? When you say fault, what is the characteristic of fault? Is it reasonable to assume the fault you assumed? If not, then we are working on a problem nobody cares. So this we got to, when we say make an assumption, before we do that, we can ask, does this assumption make sense? And the failures we assume can be modeled by either parameter change or the structure change sometimes. But the question now is really, in practice, is really like that? And how does, if this is really safety critical systems, does the industry do the same thing, right? And the control, we always assume that control is very powerful. Fault occurs, let's do a reconfigurable control. And this is, we can deal with that. But what does it mean in practice? Do you run into a problem with the saturations? Do you have enough power? When the system failed, do you have enough power even to carry out this so-called reconfiguration? And in different failure modes, how does it manifest themselves to a parameter change? When the parameter A changes to B, when fault occurs, what does it really mean? And the fault detection diagnostics, we assume that the fault detection, if your safety is dependent on the fault detection diagnostics, you implicitly assume your reliability of your fault detection algorithm is more reliable than the system you're monitoring. Okay, is this true? If you said, I have run a computer, is this computer qualified? Is this software use more reliable than the system they're running for nuclear power plant? So those are the questions we have to ask. If your the reliability of your diagnostic system is less reliable than the system you are monitoring, what doesn't make sense? So this is very important. And also, when we look at the machine learning and so on, and we assume that we have the fault data to train the models. The problem is that in a real system, well-designed system, the failure data is so rare. See, for example, Dutch railway system is running every day, how many times you run the failures? So we assume, okay, every 5 seconds we have failure data. It's not true. If you don't have failure data in the nuclear power plant, for many years there's no failure. And how do you get data to train? So that is something.
regarding the time.
Okay,
you
well,
would
I go
like-
quick. Yeah, I go
Okay,
quick.
just to start the discussion,
Okay.
we can leave some things in.
So for industry perspective, is they analyze each system component, rank the failures. If it's not going to fail, we know that if failure doesn't affect anything, let's pass. Right? And then we want to identify the most vulnerable part, then we deal with each of them separately. When we introduce redundancies has to make sense, has to be diverse, has to be independent, has to be able to switch in or with the same capabilities. And in every safety critical system design, we have to look at each case separately in a very detailed analysis, initial safety report. Then once address all the problems, and when the system is ready, commissioner, you have to deal with a very big, what you call it, final safety report to deal with safety systems. So what I'm trying to say is that suppose a temperature sensor fault, just give an example. On the academic side, we say, okay, system can be represented by AX plus BU and so on, fault occurs. But industries, they analyze every one. The connectors, what is the reliability of connector? Is sensor head, what is sensor head? The connections, what is reliability of these connections? Each of the systems, you can get the data. You can get those failure data. It's a particular sensor, they are failure data. This failure data has been accumulated maybe 20 years. If a new component goes through the accelerated test, there's a specific number. And then when the failure occurs, when you design the system, choose the system, you have to choose this system. So when we look at monitoring, I've just done for inspections, it's very important. We talk about eddy current probes, we call ultrasound, we can use X-ray, or sometimes you computerize tomography. So it's a non-touching system. You have the monitoring system should have the least impact to the operation of the system. So all those are non-destructive test methods. And the indirect measurement also, if you look at the engine oil and so on, transformer oil, those are indirect. So once you have indirect, you look at the trends, then you can estimate that prognosis will occur. Right? And the advanced technology that at our disposal now is many industries looking at the digitization. So, and then look at the different data analysis tools that were available as a machine learning, but this machine learning has to be more comprehensive. And now we need to invest some of this called Internet of Things, wireless systems to collect the data, distribute the points. So we get the data in, then we do an overview of the system. And of course, people look at the digital twins. If we have a good model, in particular, one small section of the system, we can create good digital twins. Use that as a way to have a short time prognosis, short horizon prognosis. And high fidelity models for the first principles, this is very important. We cannot just simply assume. And for the machine learning, of course, we'll put a question mark is where do we get the data? Where get data? So I think that's basically, in conclusion, I just feel that there's a big difference between academic fault detection or fault tolerance community and the industry perspective. Because industry has regulations. And we talk about different language with different approaches, with different goals. We have a different way to measure it. So in order to be able to contact with the industry, I think we need to look at what's their need, what is their approach. Right? And most of the safety critical system industries, they have regulations. And we talk about, for example, aircraft, this FAA. They don't give you the license to fly you cannot fly the aircraft. And nuclear power plant, we have nuclear safety commissions. If they are not satisfied with the way you deal with the safety, they will not give you the license. Just like you drive a car, The car is you know, if you don't know drive, you get on the road, you can kill somebody. So that's why you have driver's license test. Right? And for the car itself, if you fail the crash test, then you cannot get a license to sell the car in particular country, particular region. So all those regulations that has to be satisfied. In academia, we don't deal with that. I talked to one regulator. They are regulating nuclear power plant. They said that, you know, for us, from regulator, they don't care whether nuclear power plant can make money or not. They care about whether the nuclear power plant is safe to public. So they said, well, the safest nuclear power plant is the one that you do not operate. Just like a FAA. They said the safest airplane is on the tarmac, not fly, because people will not die. So that is their objective. So for industry perspective, nuclear power plant, we want to generate power and so on. We want to make money. So for airlines, they want to fly. So there's a negotiation going on. So to a certain level, satisfy you, a regulator, okay, so I'm happy, you know, I'm going to make some money to get the business going, get a customer to one place to another. So it's always a negotiation, always.
I suggest we move to the discussion.
Okay, yeah. So that's my 2 cents, okay?
Okay.
You have questions,
okay, let's start with the discussion. Again, we can use
that.
The next question.
Interesting.
So what are the major differences between fault-tolerant control in the academic world and that in the practical world? The answers that I will read also, they are not wrong, okay? But we would like to see your opinion about this, and it's understanding the nature and impact of faults, safety considerations versus traditional stability criteria, model acceptable for normal operations. We consider this, but they are not acceptable for actual behavior under faults, and requirements by strict regulations for safety critical applications. So what do you think? What are the major differences, in your opinion? We heard the opinion of Jing, but what is your opinion about these 2 words? They seem different, but it's good to.
Please remember, there are no wrong answers.
Yes,
there are correct
yes,
answers and the best answers.
It's just to give us your opinion, and we start. So what do you think? Okay, so far we see that the requirements about the regulations, this is a major difference.
Yeah, okay.
What do you think
I think
about
this is correct. Yeah, I think this is absolutely correct. And the regulation, that is a government rule. If we don't have rules, then it's going to be difficult. So once you have regulations, we have different companies, to suppliers, to provide the systems to support this application. But each one of them have to minimum meet the regulations. And I had the opportunity to witness certification of a control system for nuclear power plant. And they have, you know, over how can I say, many volumes of the test report. The total is probably 5 meters long, this bundled report. And then we open it up, so each aspect of the control system, they analyze what can go wrong. For example, the control system by software environment, what is the software language you use to develop? You cannot say, oh, I use MATLAB. MATLAB is not certified. You have to use a certified software to develop a safety system. And then your operating system is certified. What happens if you have failure in the operating system? Right? In particular, when you look at the safety critical applications, you have redundancies. Redundancies in nuclear power plant, we usually have what we call redundancies, 2 or 3 separate systems for safety critical application, but they're developed by different people. So three groups doing the development, these three groups should not talk to each other. You know, you cannot ask group A said, oh, how does it do it group B? You are not supposed, it's illegal. And groups, you always do it by independently. And then once you get it done, you got to, somebody got to validate your design. The validation team should not, by rule, should not have the same budget in the company. So, because what they want to avoid is, the designers spend all the money and they don't have money to validate it. Okay, it looks good. Okay, I sign my name. It's not allowed. So, all this make sure you don't have common mode failures. Because so if you use the same computer, same Windows system, what happens if Windows system has a bug? All three has similar bug. So this is not allowed.
Okay. Yeah. Don't. There is no reason for permission. You can.
But I found super interesting when you said that the most safe nuclear power plant would be the one that is not in operation. Yeah. For the railways, it's similar. It's similar. In the standards, it's mentioned that the railways should operate safe and being available. That is because if you purely optimize safety, you ended up that it's better to not put people in those huge vehicles, going in such a high speed, because something can go wrong, you can get accidents. But then, after this decision of, okay, let's operate it, then you do a compromise with safety. Yeah. And then that depends on later how much room you give for operation while being as safe as possible.
Yeah. That's what I'm saying, negotiation between the companies and, even the drugs. FDA, they have to prove the drugs. If I'm a drug company, I develop a drug, it's very good to cure the cancer or cure something. And FDA, we look at what happens if there's some side effect that kills somebody. That is more important, not the bigger population. Even though you have 1,000 people with this drug potentially cure, but you can kill one person with this drug. As FDA, they look at one person, safety. So that is safety.
And there's one more aspect on for instance, for the industry. You don't have a validated model, you don't have data, then basically the best you can do is to do some voodoo or to try to guess with some cards on, okay, what's going to be the future behavior. So, and then they don't do that. So they are very conservative. While from the academic's perspective, then there are know-how and let's say, analysis of new models to try to explain those unknown situations. Yes. But then, there's no validation, so how much can you trust on the model? Is it conservative or not? Yeah. How to include it in the
It's very serious business that we're just talking about today. If you said, I have a new control design for the aircraft, I did all the MATLAB simulations, everything is done. So today is the day to test flight. Regulation is that you design the controller, you go with the test flight on the flight. You fly. This is so do you put your life on the line? You cannot say, I designed something, maybe I'm not going to fly. I do not think this will work. You go. It's not like that. Trains, the same thing. You design new trains or you sit in front.
Okay. Sorry, Luis. And then obviously.
Yes, thank you for your points. From my point of view, it is good that the academic world and the industrial world is not doing the same. Why? Because the academic world is here to propose, to imagine, and of course on the industrial side, all these safety regulations are very important and the engineers must take care of this. But there must be, at some point, new methods, and of course, many of the methods that we propose will never be applied, but some of them will, and so that's why we are here.
Yes, absolutely. This, I know that just recently, in the last few years, the nuclear power plants, they are looking at the monitoring, set up monitoring, looking at collect data. They collect all the data. Sometimes they do not know how to deal with this data. So look at the algorithms to analyze the trend, this data. This is originally from academic, and then for maintenance, it be very useful. The condition-based monitoring and so on, because they have all the data. Yeah, it's true.
These methods are like 10 or 15 years old.
Yeah.
Trend analysis and all this
Exactly.
stuff.
Yeah.
At some point,
But now we have analytic data, analytic method, so on. We can extract the features easier, so on. So that is something, we can. It's somewhere we can work together.
And because we are forming also new generations, and then they are sometimes also more pushy. They know better later on how to even further the boundaries.
So to continue on this discussion, as you said that for the industry, especially in the initial phases for during design, at the component level, they look at risk, they create a safety case, they do risk assessment. But for the designer, or at least even in academia, we do not think about regulations or risk assessment until it comes to validation. So my question would be then, is there a way to maybe more seamlessly include all these factors, the risks during the initial design phases for us as designers of systems?
Yeah, I strongly feel that at our undergraduate education, maybe the final years, we should introduce students the regulations, the concept regulations, show them, the standards, industrial standards, and so on. I think this is a very important part of education. And before I got involved in this, I did not know. To be honest, I did not know there's so many regulations, so many industrial standards, so on. And you look at IEEE standards, IEC standards, all those standards you have to meet first. That's a minimum requirement. Then on top, for each industry, you have regulations. Right? So industry want to go beyond the regulations to build some safety margins for safety critical systems. So this is very well taken.
In that context, in France, at least, I can tell you that in the engineering schools, such as Polytech Nancy, when we train students in the domain of reliability of systems and so on and so forth, in the first year we introduce them to the norms that are standard, and now we will start especially working in the nuclear sector, which is one of the national policies starting from next year, and there we do intend to expose them to the standard norms that exist in this domain.
Here we go. Okay. Thank you, that's great.
Okay, very nice presentation. We need to move a bit, but we can come later if there is time. So we saw very nice applications. What is in the? There is no need. You can.
No. There are more questions.
Yeah. We can change. Now we will see a bit about more on the academic side. No. We will skip the questions for the time being. Vicente can continue, and we can come back later on this topic. Just not to continue on the same thing, to see different aspects. So Vicente is going to talk more about a new, let's say, way of doing control, considering maintenance aspects, health-aware control of complex industrial systems. So how can we include information of maintenance, of prognosis in a control context? Is this correct?
This
okay,
is
let's see.
Correct. Okay, so I think that some of the ideas Baso suggests at the point, is when my young comment. I mean, in our community for a long time, we have been working, it was discussed before, about detecting faults, about reconfiguring the system once the fault has occurred, fault-tolerant control, basically. In the industry, when we detected also this interest, also it's presented at the very beginning for some of the panelists and Farbaso and other people in the conference as well. There is an interest in And this is why the title of this panel, going from diagnosis to prognosis. No? Prognosis in the industry is perceived like something more interesting. I mean, they are interested in diagnosis, but when you talk about prognostics, they open the eyes. No? And, but okay, the point is that in our community, additionally to do prognostics, there are communities also dedicated only to prognostics. There is the PHM community that is specialist in prognostics. Of course, we're interested in prognostics, but here the idea is how can we use the information of prognostics to improve the control. No? And this is a discussion, long discussion, I remember, with Didier Tellol. Unfortunately, couldn't come here, and we invent a bit this idea, no? That other people also use now, that health-aware control is to take not faulter and control. Faulter and control, maybe there is a picture that clarifies this. I will go directly to the picture. 1 minute, I think the picture is coming. In the faulter and control, 1 minute, because I have too many materials. I will go directly to the place where I wanted to show. Exactly, it's here. In fact, it's this picture here. Up to now, at least in the SAFEPROCESS community, we try to do diagnosis from many of the methods you know, and you want to once you know the fault, you want to reconfigure, accommodate the fault. This is the classical approach. In the kind of control we are talking now, we think not on that. We think that we have some model, in this case prognostics, that is informing about when the fault will occur. Is what it's called in the prognostics terminology the remaining useful life. No? How long the system will operate under some acceptable performance. No? That is a bit what the remaining useful life is assessing. So the idea is that if we have a method, an algorithm, that tells us this system can operate for 100 years, let's say, or 50 years, whatever horizon you want. Okay? So, but this is now. Okay? If you operate the system in the right manner, probably you will arrive to this horizon. But if you are very aggressive, you want to do a lot of profit now, it's bread for now, hungry tomorrow, then you will accelerate the degradation of the system, and this nominal remaining useful life that theoretically was 100 years will be maybe the half. So the idea of the health-aware control is about adding in the controller an additional specification, additionally to the performance, that is the classical one that we use in control, that takes into account the remaining useful life. So the idea is that we have to achieve a kind of trade-off. Trade-off in the sense that, of course, we want the maximum performance, it's always that, but taking into account that trying to achieve the maximum performance will represent a big effort, probably, in the systems. For example, this is very clear in the wind turbines. In the wind turbine community, they don't call this kind of approach health-aware. They call fatigue or similar names approach. So there is a kind of trade-off between extracting the maximum power, in the case of the wind turbine now, but minimizing the fatigue. This is a kind of the principle. And this that can be applied to the wind turbines, applied to many systems. I mean, the original idea probably is very simple from that field. But the idea could be extended to a water network. For example, if you have several pumping stations with different reliability, here we connect also with the concept of the reliability. We can take into account how the operation of that network or that infrastructure in general, and also related to your talk at the beginning, the manner you operate the system can enlarge the life. So that, and this is connected to what Basso said at the beginning. When we design a control system, we can add some additional objective. There are techniques that are quite straightforward to do this. Techniques based on optimization, where you need to add just an additional goal in the controller. You have one goal that is the maximum profit. So you can add an extra goal that tries to take into account the extension of this remaining useful life. So this is a bit the concept of the health-aware control, that merges prognostics with control, and it's very different from the control and control that we classically work in this community, where we have to do some reconfiguration, but after the fall. This is to prevent the apparition of the fall, but taking into account that we can decide a bit on when the fall will appear. And this decision is this trade-off between maximizing power and minimizing maintenance costs. So it's related again with the maintenance. This is a bit the point.
Thank you, Vincenz. So we can change to the Mentimeter. This time we went a bit more brave with the newly crowned expert of our time, ChatGPT, and we asked it to provide the definition of health-aware control. So we changed to that slide. Probably you will see the definition on your phone, but I will also narrate it. So what is health-aware control? And the answer is health-aware control is an advanced control strategy that integrates real-time system health monitoring and management into the control process to optimize performance, prevent failures, and extend system lifespan. So, do you agree, disagree? Let's see some votes. The definition on yourself.
Because it's a different type of question.
I see.
You press on present.
Yeah, I understand.
On present, and then we will go.
Yes.
Sorry.
Yeah, sorry for the technical issues.
Ah.
First time.
It's our first time. Now we should be able.
It seems we weren't full
To
tolerant
what
enough.
extent? Now, I'm not sure how we see. Shall we click here?
Not us.
Yeah.
You can scroll.
So you see the cursor and it's giving the answers in real time. Yes. We should have provided a wrong answer. Then it would have been more provocative.
Yes, that's true.
Okay.
Let's say, besides this, what is your opinion?
Yeah, so if you don't agree 100%, what is your different opinion? Does anyone want to comment something on this?
It really depends on the way you define profit for the company, I guess, because at one point you are trying to maximize your efficiency, right? So on the contrary, you want to have the longest lifetime for your component, and that would lead to so-called minimax optimization, I guess, where you're always dealing with saddle points. They're super, I guess, I haven't worked with them, but my intuition would be they're super unstable to optimize. And then depending on what you define your time window to be, depending on the project, depending on the component you have, for example, for production assets in industry, for example, you have the 5-year time span where you have your return of investment for predictive maintenance. For different ones, I guess for transportation, for railway, you have longer years, not 5 years. I'm not sure how long that will be. So depending on your field, I don't think that you can always include the fact that you want to have the healthiest state and maximize your profit, because for many components, especially as I said, production assets, you have very short lifespan, so you really have to push the limits and have your performance there. But to ensure your basically profit, you have to have these maintenance schedules that are optimized to reduce your downtime. So from my experience, companies don't really care that their components go bad, they care about the downtime. So they're not really basically giving so much attention to the components themselves, so sustainability and stuff, not really a thing. More, they are producing less, they have more downtime, not the component life itself. So that's my intuition, I guess.
Another view.
Yeah.
Can I come in here, Visons?
Yes, go.
So it's interesting because I believe, well, it's my point of view, but I believe we all agree in this community. So it's really application based sometimes. Let's take an example of a drone or autonomous car. So let's say a drone needs to accomplish a given mission. And the battery, which is the energy source, undergoes degradation as a function of usage cycle, but also as a function of environmental conditions. This is a typical example I usually present to illustrate the essence of health-aware control, where you need to optimize on the performance of the drone, taking into account the degradation of the battery. And here, if your mission is safety critical, that is, if your mission is really essential, you must ensure mission completion. And the only way to do that is by optimizing on the degradation rate of the battery. So that's a typical example where.
If I may build on top of that, for drones at least, there's a theorem that says how fast you should be with your drone for you to financially make sense to use drones. So if your limit is less than that, then you cannot really financially basically justify your claims. So from that point of view, but for mission critical systems, I can understand. But again, if you want to make sure that it happens, then you are not really doing health aware, you are really putting the limits way before the limits of your physical system. Then again, you're far away from that saddle point. That's why I basically made a claim.
That's an interesting take.
I think if you Google from Professor Scaramuzza, he has a theorem about how fast you should be with a drone for you to actually make sense, given the battery capacity.
I think the difference is between this production system from safety critical system. Safety critical system means we do not want the failure to occur. For production system, there's such thing as run to fail. You just run the system as long as you can go. Like your light bulb, at home, you don't change it, for a certain period of time. Just let it, when it goes out, you change a new one. So it's run to fail. But the safety critical, if this light bulb is, for example, at operation table, you don't want to take the risk that during the operation the light went out. So you want to make sure it's, you change it based on either time maintenance or the condition-based maintenance. That has to be done. So this is safety critical application versus the ordinary production system. So I think you got your point is well taken.
It's a very important point, and just to add and perhaps bond with you. So the example that you give is typically the production systems, right? Here, I agree with you. The prognostics and these notions may not make so much sense. Perhaps what would make sense, and please tell me, would be the reliability of the system that would particularly take into account your MTBF, the mean time between failures, MTTF. And so the idea would be, remaining the same philosophy, idea would be to optimize on the MTBFs, optimize on the production efficiency so that the MTBF, mean time between failures, is reduced. That would be the idea. So I believe while depending on the application area, while the way the problem is formulated would be different, the overall philosophy would remain the same. How you would inject or integrate the reliability-based information within the control loop design or the policy reconfiguration strategy.
Just to clarify, I'm totally on your side, but when you go to companies and talk to them, they say, I have a perfectly functioning preventive maintenance solution. Why should I invest so much on sensors and solutions, the DevOps, the maintenance and everything, to change that to predictive, knowing that right now I do not have downtime, I can produce as much as I want, I do maintenance on the weekends or when I don't have the shifts or the heavy shifts. So this is the question that I want to bring up, how can you, from a financial point of view, really justify your solution? Because that's a lot of investment. Just imagine you go to a pharmaceutical company, they have to validate, as you mentioned, the whole system, that you have installed the sensors, you have redundancy if you need, then that would be the case that you really cannot convince them to go from preventive to predictive. But again, I'm on your side because that's also what I research on.
I like very much this new definition because it captures somehow the multi-objective nature of the decision making. Sometimes it's maintenance also depends on the logistics. Do you have the qualified personnel available to do it, or do you want to reduce CO2? So there might be much more or many other objectives at the same time. But then there was one aspect that I found brilliant, how you explain it. Then when jumping, let's say, from the, you mentioned the predictive maintenance, somehow you have the balance between performance and cost. But with prescriptive, you are changing the game. You are changing parameters in such a way that the system now is almost a new one. And that allows you now to push this Pareto front towards a better optimal if you do the right decision. I think that concept of prescriptive maintenance, how, because now you know the trade-offs. That's the operational how it works right now. But when you introduce these techniques on root cause, on the lifetime prediction, then you are changing the game. You're changing then this Pareto front that you typically have. That's my opinion.
Just wanted to add, so speaking from sort of the perspective like a wind farm, which I guess is a production asset, health-aware control and prognostics can be very valuable. For example, the maintenance on an offshore wind farm is very reliant on the weather. If I know for the next month the weather's going to be bad, I can't get out and do my maintenance, then I can make sure that I'm controlling the wind turbine degradation in such a way that it won't fail within that month, and then I lose all of that production in that time period before I can actually go and do the maintenance. So it sort of ties in with your maintenance planning and scheduling as well, particularly when it's constrained by external factors like that.
Thank you. I was actually, I'm not sure if it's a question, but more a comment because the control is more real time, while degradation is a slow process. So it's hard to measure how should you prioritize degradation versus control. Because, I mean, you take the example with an electric vehicle. If you stay within a certain state of charge, the battery holds. I mean, it will not degrade. But if you go beyond either it's too charged or it's almost empty, then it degrades. But how to value this, it's very hard. I mean, that was more a comment than a question, because it complicates the things.
Bueno, complicates in which sense?
I mean, how do you, in a real-time controller, value, should I do this? I mean, the impact on aging.
You need to model, you have to create a model of degradation in function of the control. It's like augmenting your model, no? That describes the typical normal dynamics with some additional equation that reflects the manner that you control, how it affects the life of your system. That's the point. No? So you have to augment the model with extra, let's say, equations that reflect the manner you control the impact on the remaining useful life. And I agree that it is an extra complexity, of course,
yes,
but what is the benefit? That you, in the short term, it's clear that there is no benefit. As you say, you need to see in the long term, no? Because you will extend the remaining useful life, and your machine or your system, no, that has to last for 10 years, no? As the manufacturer guarantees, no? You will achieve this goal. If you are very aggressive, probably you will have only the machine 5 years. No? So it's the long-term profit. And I understand that in the short term, even you can lose a bit. I agree.
I would like to say one little thing. We tend to think of the moment of maintenance like the decision moment. But actually, every day that you decide to do nothing is also a decision. Do nothing is the decision. You're deciding the whole time.
The question is where we were taken. If you look at the depletion of the battery, and that is a process. It's not a safety critical. You know, you're fully charged. Then as you run, the battery becomes less and less. But for electric cars, what is the safety system? Is the brakes. right? You have a foot brake, you also have a hand brake. So this hand brake is a redundancy. This, if a foot brake fails, you lose hydraulics or something, and you can use a hand brake. But the battery or the gasoline in the car, that is a slow process. So it's a different, not safety critical.
Just to...
There are some examples like the pipelines, the distribution. Usually what in some countries and Mexico they do is they optimize by making a batch process. It means they give you water to one part of the city and the other they don't have. And this, after a while, they damage the pipeline because you get strong pressure because it's empty the line. Then you get pressure, and then after a while you don't get nothing. And then next week maybe you get water. And this produce, they know now that they produce so many holes and faults in the system because really, the system is not designed to work so in this bachelor process. And they do it because we don't have enough water. But at the end, we have nothing because all the pipelines are damaged.
Christina, this is a very good point. In a nuclear power plant, again, you cannot change the power. Okay, you cannot change power or you keep a steady state operation. For the airplanes, the safety critical system, you can only have a number of takeoff, number of landing. I don't know how many, but after, even if a new plane, if you go up and down, then this plane cannot fly anymore. There's regulations. So for the water system, the same. You cannot, do that transient, because transient is the one hurt system most.
But for example, following your example, in a controller, in a classical MPC controller, for example, you add this term of the delta U that basically takes into account what you say. If you don't put the delta U term, your controller is doing bang bang. But if you put the delta U, then you smooth. No? And this effect is to avoid the situation you say. No? That at the end the control produces the same. But in the sense that the function, the water arrives. But in one case, your infrastructure, as you say, in maybe months or years, there will be a lot of leaks because of that bad management. So the control functions, do the function, but at the price of maintenance. Exactly. Well, it's the same in other controls. In another controls is exactly the same. That there are some controls that do not care about this. So, but the point is that not only this, of course, that this is the simplest manner of doing, because in the MPC this factor is already considered. Here we are suggesting a bit more than that, in the sense that if you are able to characterize how the control degrades the life of your system, this is the concept of health aware, you can find a policy that additionally to satisfy the goal of control, supply water, for example, you do in a manner that you don't degrade so fast your infrastructure. Exactly. That's the big challenge. That is the big challenge. Exactly. That's the big challenge. That, for example, is another discussion we had with some colleagues. Prognostics, from my knowledge, is very good in what we saw in many papers here in the conference, in evaluating the degradation of a component. When you have a system, it's more complex because it's not only to characterize a component, you have to characterize the degradation of the system. And passing from a component to a system is not obvious. There is if you follow more the classical way, reliability, they have some component composition rules that you can systematize. But you have to follow the reliability approach. But in the prognostics, it's not, from my knowledge, probably there is someone that knows more than me, the composition of the state of health of every component, how affects in the system, still is an issue. I mean, all this is an issue. Still, I'm not saying that this is solved. I'm just posing here a problem that could make interest.
Yeah, maybe for the sake of time, we can move on to the next presenter, Mayan.
Yes, exactly. Bueno, the politicians in reality don't care.
It's a Boolean variable.
Exactly, exactly.
So my young will give us a presentation about deep learning-based prognostics and safe control learning. And the floor is yours.
So very quickly, my name is Mayank Jha, and I'm working in the areas of deep learning-based prognostics and safe control learning, which might seem two distinct areas to you, but as I'll show you, they are complementary when seen in the holistic or comprehensive framework of health-aware control learning. So, you know, prognostics, we have two basic approaches, two basic goals, and two major goals: to assess the state of health of the system and produce the forecasts of remaining useful life. So these are two major goals, but then again, a quantification of the uncertainty and so on and so forth, they are also pretty important. But basically, in prognostics, you want to assess the state of health with a certain level of accuracy and generate the remaining useful life predictions based on the degradation trend. So since 2006, 2007, a whole range of mathematical tools have been applied, including regression, nonlinear regression techniques, estimation theory, starting from Kalman filters, extended Kalman filters, unscented Kalman filters, particle filters, where essentially you are able to estimate the nonlinear dynamics in the presence of non-Gaussian, non-additive noises. So that has been fairly well accomplished and till 2015. So, you know, one is able to, in principle, estimate the state of health with confidence bounds and generate the rule predictions with confidence bounds using estimation theory. Since 2015, 2016, we see an extensive use of deep learning-based methods to accomplish exactly the same goals. And that's probably because of the advent and advancements in the area of deep learning since the emergence of AlexNet in 2011, 2012, so-called the modern deep neural network. And so we see an extensive augmentation in the use of deep neural network structures, which are able to provide the mapping. You know, deep neural network structures, they are excellent approximators. So we are able to learn the nonlinear dynamics in stationary or non-stationary situations simply by feeding in the sensor input data and performing the supervised training with respect to labeled RUL data. So typically here I show you an architecture comprising of CNNs, convolution neural networks, where we have a set of inputs coming from sensors, which may be noisy, non-stationary, multivariate, and whatever you want, comprising of any distribution you want. And essentially we are able to understand the mapping, the relation between the inputs, such inputs, and the rule, the true rule. And here, although I show you one structure, like convolution neural network, essentially we can replace it with any structure. And then in this context, a lot of, well, that was to wake you up, guys, huh? Mr. Sound, the guy. He saw some of you sleeping, huh? So, so although here I show you convolution neural networks, but there have been, as of today, there have been a wide range of structures have been used, including convolution neural networks, LSTMs, recurrent neural networks, and their variants, combination of CNNs and LSTMs, and just recently, yesterday, we saw transformers and MLP, their combinations to perform the same mapping. So here I show you another pipeline. You know, we have a set of inputs, 3D tensor, and using LSTMs, we are able to understand the relationship between the inputs and the rule data, the rule value, right? And so there are also works that combine the CNNs with LSTM. So you might ask why CNNs? Because CNNs, they are very powerful. Yeah, they are pretty incredible in extracting the underlying hidden characteristics, which may be heavily tangled. Basically, you can understand the representations that are helpful in understanding the degradation pattern and eventually relate them with the rule data. LSTMs, they are excellent in understanding the sequential behavior. So how the data changes over time, these dynamics, you can understand with very good efficiency. So yeah, so that's about deep learning-based prognostics. What is safe control learning? So safe control learning is an emerging field. In last 5 to 6 years, we see an extensive increase in this area, where the objective is to learn control laws that assure stability, optimality, and safety of systems. But safety of systems in a very large sense. For example, you want to keep your car in the middle lane of the road. So you want to assure safety in the sense that the car shouldn't go outside the road bounds, right? You want to learn a control law that helps the drone to go from position A to position B, but hey, avoid this particular trajectory, because you might crash into the wall. So that's safe control learning in a very, very broad sense. And that, for example, such a kind of objective has been achieved using MPC. Typically, the goal is to ensure that the safe set remains invariant. That is, once your system states are within this safe set, they remain within this safe set till infinity, till eternity. So that's the idea. If you formulate the problem on an infinite horizon, that typically it's exactly that. So typically, the idea is to learn the control laws that ensure safety, stability, and optimal performance. Now, I find it quite interesting because we call it safe control learning, and we are SAFEPROCESS community here, so there is definitely some link. But let's see what's the link. So typically, when we talk about health-aware or prognostics-aware safe control learning, what we are looking at model or data. We are looking at the degradation process. So I'll not go much into details because you already explained that. So being in the same spirit as Wisson's, so we are looking at the degradation evolution, degradation mechanism. We are looking at the reliability assessment, for example, or prognostics, where we are typically assessing the remaining useful life. And we want to design the controller in such a way that the reliability is increased and the remaining useful life is extended. And typically, if we do not have a good knowledge about the model, typically if we only have data, typically if we have highly nonlinear dynamics and also nonlinear degradation dynamics, then I believe what would really turn out to be efficient, not the traditional classical model-based approaches, but learning-based approaches, which typically can be formulated in the safe control learning paradigm. So that's to initiate some discussions on these two axes, and also perhaps motivate some works in the future, combining all these elements where the reliability levels or certain rule is guaranteed in the learning paradigm. So let me move to.
There is some. Yes, we can pass to your favorite meeting again. This time we have some.
There is some question over there.
Yeah, please.
Thank you, Mayank, for a great presentation. So I also would like to make a comment to try to connect some of the discussion that we have had here. So usually in the field of prognostics, people mostly care about time to fail, when your system is going to fail, right? So in the in the SAFEPROCESS community, we commonly talk about faults. Faults as a deviation of a property or characteristic of your system. So in the prognostics community, your system could experience a fault and still operate. What you care about is when it's going to fail, means you cannot use it anymore. So there is a subtle difference. So if we look at it from the moment when your fault occurs in your system, there are certainly some similarities between fault-tolerant control and health-aware control, like Daniel was mentioning before. So it's a bit blurry in that sense. And also, with respect to your comment about the industry, it all depends on how you define failure, right? So many industries, they look at performance metrics, and they care about performance metrics. For example, they want to keep production above a certain level. So for them, end of life means when their production goes below a certain level. So what they care about is trying to predict when the system is going to reach that state. And the system, the system as a whole, like Vincent mentioned, it's a system of systems, right? You have multiple components, how to account for the interactions between them. When your system performance as a whole is going to reach that point. So in that sense, I think it's a very challenging area to try to control the system in a different way. Why? Because control usually occurs at a lower scale, at the component scale. But you care about the performance of the entire system. So I think it's an exciting area, but also very, very challenging, because mostly people look at this as a maintenance problem, scheduling problem, right? Like you said, when do I schedule my maintenance? But they don't pay a lot of attention how you control your different components in such a way that you can prolong the performance of your system. So you can keep production above a certain level without having to stop, even, on a weekend to do maintenance. Yes.
So just, so thanks for that comment, Marcos, because indeed we need to understand that faults, they are not similar to degradation. Degradation is a slow dynamical process that may be different and highly different from the dynamics of the system. And typically here we might be interested in detecting the fault, but what we are also mainly interested in is following its evolution, making forecasts, that's right, and modifying the controller in advance, in a proactive sense. So that way, then there is relation, because you want to detect perhaps the initiation of degradation, but it remains distinct from FTC because you want to follow the evolution, make some forecasts, and modify the controller in a proactive manner. But you want to correct me?
Yeah, it's like this.
For a fault, it could be the rule for losing some performance, etc.
No, it's general.
Yeah, it's not necessarily the death of something. And then another remark I want to do is that I don't agree with this goal to have a rule for the whole system. I believe it's more important to have them for the different components, particularly for those that you can change, not the system as a whole, and also taking into account the criticality of the components.
I agree with you. What I'm trying to say is that typically in the prognostics, you focus in a component, no? In a particular component. Imagine that you have a network with many components, and even they are redundant, no? So how you distribute the effort among the components, no? That's a bit what you say, because there are some components that are more critical than others, no? But to reflect this, no, in the control is what I'm trying to say that is not obvious, unless you have a model, for example, based on reliability or whatever technology that allows to compose, no, the criticality, no? That's a bit, no? Because if you have, for example, parallel pipes or parallel, no, no, you can. Is this information you say is there?
There may be an interaction.
Exactly.
Of the rules, of course. But having the rule for the whole system is
Bueno, in the sense that, for example, in a large infrastructure, no, is you have a guarantee of service, let's say, no? You have to guarantee that you can no, provide the service, no? And then this indicator is if you will be able to do the service. And for doing the service, it's not enough to say a single pump or a single component is, no? You need, because you have many options. You have many options, no? You have many paths. No?
Parallel or series connections.
Sí, parallel series, no?
So in that context, while in the reliability, the domain of reliability, these kind of questions have been fairly well resolved, like, you know, parallel connections or series connections. We are able to propagate the reliability from the component level to the system level using tree-based approaches, in French as we call Abdel de Fayence. So we are able to do that, but while we are able to do that in reliability sector, still in PHM area, if you would agree, most of the works, they remain confined to the component level. Only few works exist, and they are emerging, as we saw, that target rule prediction on a system level, and that's because it's still a challenging problem, because even if at component level the degradation is, let's say, linear, the prediction is never going to be linear. The prediction is going to be essentially non-linear, simply because there is interaction between different components. So it remains a challenge even within the PHM community. And so for us, of course, it will pose a challenge at the prediction level, but also its incorporation in the control closed loop will be not so easy. So I agree.
Because, for example, in the case of a system, when you create the control model, the interrelations exist.
Yeah,
no? You decide.
It's a coupling.
It's the coupling.
Yeah.
No, it's not.
And if you consider this dynamics non-linear, then it's.
I will give you a very good example. You talk about the parallel, you know, the series. I'll give you a very good example. We have to look at the components. You look at ourselves. You look at yourself. I look at myself. You know, the person consists of many components. Now, medical advances that if your knee is broken, you can change the knee. Your hip is broken, change the hip. Right? If your liver is damaged, you can do a liver transplant. If your kidney is gone, you know, you can change a new kidney. So those are component-based. But certain components, your brain, if the brain dead, you cannot transplant somebody else's brain. So then the system is gone. So that is a very critical part. So it's all component-based. You cannot change the whole person, but component by component. And for each component, they are depending on how you abuse or use this component. That component, the lifetime is different.
But I think, so I'll take a different take here. Yeah. I think what we are trying to highlight, and please correct me, is while component-based decision or component-based forecasting or prediction is fairly well accomplished, still on a system level, to assess the component degradation at the same time is not so obvious. It's not so established for the moment. So I believe there's a lot of work, and especially to include the prediction within the closed loop is not so easy when we want to do it at a system level.
You need to maintain your knee, right? You need to maintain your hip, maintain your heart.
You're the nuclear guy, so I know your approach.
You need to maintain.
So let's move to.
I just because I mean this discussion we talk about components as part of systems, and I just wanted to add that when we think about our truck fleets, it's another level as well. I mean we have a system of trucks or assets, and I think that is also quite interesting aspect of this in terms of control system, because we do transport mission planning, and I mean. Then you can really choose. I mean, if you know that you have a lower health on a certain asset, you wouldn't maybe select the more dangerous or the one that will wear out your component the most for that vehicle. So I think that sort of control system is quite interesting as well. And I don't know so much about these like electrical vehicles. We are in the beginning of that at Scania. But there is also the decision making. It could be that you optimize on a fleet level. If you see early on that batteries degrading, maybe you can swap it between the vehicles in the fleet to sort of make sure that it will work for the full length of the vehicle for all the vehicles. So I think that sort of system level is also interesting to take into account, and especially when you are mixing these concepts.
Yeah. So using reliability-based assessments, we are able to do that. We are able to look at the reliability of each component and propagate it so that comprehensively we look at the, as Visan said, the service provided by each component is accomplished, like the system function is accomplished. You asked me to choose one question.
You can choose one question.
Yes, I would not.
I agree about your comment about the drugs, and I would say the same is also for the marine vessels. That they are under the trip for many days, there is something to be done. At some point they need to do maintenance, but they can do maintenance immediately, and they need to stop at port, the first port, but they can go long.
Actually, some trucks that operate in the neighborhood, some of them we send from Sweden out to South Europe.
Yes, it's about planning. Yes, please.
So with the Mentimeter, which is the main challenge of deep learning-based prognostics? What do you think? There are no wrong answers. Again.
There are no wrong answers, but there is one winner only. So the first option is dependency on labeled rule data. The second option is need for large training data sets. The third option is long training time. And fourth option is interpretability, explainability of as it exists. The obvious candidate is winning.
There's a new paradigm. I mean, it's been already like from a couple of years that there are researchers going for this database approach, combining with the physics. So then somehow you have some data points that you train your network.
Pins.
For instance, the pins.
Yeah.
While you have still unexplored regions where you can rely on a physical model that you can fill up with some more information, but then if the model is not validated, or you have a very low, let's say a lot of uncertainties in the dynamics or in the practice, then you might be filling up information with wrong ones. Then it's all about experiment design. What's the right, how much can you value the data that you have, and how farther away can you still predict?
Yeah, the pins, the physics-informed neural networks have certainly facilitated the training of deep neural networks by through the augmentation of physics-based knowledge in the loss function, and that has also come in the prognostics area through the works of various teams. And typically they tend to reduce the training time, but how much they help ease the dependency on labeled rule data, I'm not aware. But typically this remains a standing challenge today, because the architecture that I showed you, sensor inputs, and hey, output you get as rule estimation of rule, it's not so easy if you don't have a large data set with labeled rules. Labeled rules imply you are degrading your system till failure n number of times. You can do that 2 times, 5 times, 10 times, depending on the severity of criticality of your system. But hey, can you degrade your system 1,000 times? Can you do that 10,000 times? Yes, you can do that if you have a model. But in real life, that doesn't happen. As you said, in nuclear sector, you rarely have failures. Enrich our training data sets, and we came up with some strategies to make some predictions in the absence of labeled rule data. So typically, today, although in principle, using all these heavy, monstrous deep neural networks, we are in principle able to make this link between inputs and estimation of rule. But in real life, that doesn't happen because you do not have so much of a labeled rule data set. So that stands as the major standing challenge today. what I can also say is that need for large training data sets is a problem across machine learning, but also AI and sorry.
For diagnostics.
For diagnostics, the same problem.
It's the same because you need false signatures, right? And you need to invent them.
Yes, and you invent through that augmentation based on a model. No? So
that's right. So model is biased, so your signatures are biased, and your training data set is biased. So that also remains a standing challenge. I believe nobody voted for a long training time because all of you have access to GPUs if you have money, yes. And I believe the interpretability, there are now approaches in the explainable AI domain where we are able to assess the sensitivity of inputs to the given outputs, but I believe the deep learning based prognostics still remains largely a black box approach where the outputs or the learning is really is not really well understood. But with PINs, that is physics-informed neural networks, that might just be, we might be able to reduce that, because if you augment your training process with physics-based knowledge, somewhere you are able to interpret, your outputs because you have a knowledge of model embedded within. So yeah.
Interpretability and explainability. Are these important for certification?
Absolutely. I think that's the way ahead. There are two basic needs for certification. First, to ensure that the robust, that is the outputs are bounded. That is we have how to say if we are able to ensure the error, ensure that the estimation error is bounded, if not zero, then we are somewhere able to ensure the requirements imposed by certification agencies. That's the first point. Second is, if we are able to interpret and the decision-making process, that will certainly help the safety, the certification process.
Okay, thank you. So I think it's about time to conclude and finish this roundtable. Are there any comments that you would like to discuss here? Yes, Christophe.
Perhaps concerning to answer among the possible answers to the previous question, and regarding a data set, when we talk about a large data set, we can understand large with the number of samples, the number of available samples. But perhaps the question is also what kind of data, how to feed the deep learning universal approximators, how to feed them with what data, because we mentioned systems. Systems, it is we can view it as a set of components, but it is more than just the addition of components. And what data are relevant to describe the degradation process. We can observe things, but what kind of data are relevant to characterize the degradation rather than its consequence? So that's...
So Christophe, that comes down to the same comment of false signatures.
Yeah.
You need to have enough training data set which is rich and diverse. That is, you are able to show the neural network various scenarios. So that's relevant in fault diagnostics, but also in our case, because what you say, and I fully agree, even means that we are able to show the neural network different degradation patterns or degradation mechanisms under variable operating conditions. That may be true in some cases, that may not be true. That is, if you are really able to degrade your system till failure under various seasons, under various operating conditions, you have a good data set, but that's not true in real life. And so I fully agree with you. That's not always the case. When we talk about industrial systems, that's not always the case. You have, let's say, degradation of fuel cells. So fuel cells, they degrade very rapidly during hot season. When the temperature, when it's summer, when the temperature is high, the degradation rate is fairly high. In winter, that's not the case. And if you look at the degradation curve, you will see severe nonlinearity. And depending on the season, the pattern is very, very, very chaotic and very highly nonlinear, and also non-stationary. And in such scenarios, deep learning fails miserably, because you just don't have enough data, and you have few trajectories, and they are highly nonlinear. So you cannot understand the pattern. In such scenarios, my experience with estimation theory has been pretty good. So because you can simply propose some approximate degradation model and fit your data. And if you are working with particle filters, essentially you get good estimation and good prediction also. So it's really a question of availability of the training data, but also a question of how gentle how gentle your system is. If it's very nonlinear, it's going to fail.
So somehow it seems like we are moving from a period where it was big data, the buzzword, trying to solve a lot of problems, into now an area where it's about few data, few good quality data, how to embed this into the learning process. Then you get different challenges.
Okay, thank you very much. Time to finish this round table. So your feedback is more than welcome, because not only content-wise, I mean scientifically, but also about this round table, if you want to see it in the next SAFE process, something like this to encourage more round tables, or ideas of how to make it more interactive, it would be much appreciated to hear from you. Thank you very much for joining. Thank you for expressing your opinion and having nice discussion. And of course, thank the panelists that agreed and they gave their opinion, their scientific view about this interesting topic: control, prognosis, diagnosis, and maintenance. Thank you very much. Enjoy the gala dinner in 1 hour. Thank you.